my name is Mengmi. I'm a PI of Neural Cognition Lab from STAR, and I'll also be taking a joint appointment as a tenure track assistant professor starting from July 2023. So there are multiple PhD scholarships and the postdoc positions opening. I don't want to steal anyone from RIKEN right now, but if you happen to know someone who is interested in such position, please feel free to let them drop me an email. All right, let's get started. So for the past few decades, especially for the recent years, we have made tremendous progress in AI. From playing the game of Go to even developing large language models such as ChatGPT. However, I would still like to argue that this current AI system still lack cognitive mechanisms that can address tasks that are fundamental to human intelligence. So now let me illustrate this by giving you an example. Imagine that you are a visually impaired person named Michael, and what you can rely on is an AI personal assistant. It can talk to you and describe this visual world for you. So what do you want this AI to tell you about? Well, you certainly want your AI to be attentive about the surroundings. For example, you want your AI to tell you that there is a chair and a table in front of you so that you can avoid colliding those. But you certainly don't want your AI to tell you everything about the environment, such as there is a car parking on the opposite side of the streets, which is completely relevant to you. Second, you want your AI to understand the environmental context. For example, you want your AI to tell you this is a busy street, so you can expect cars, pedestrians, but you shouldn't be expecting elephants working beside you because this is not a jungle. Third, you want your AI to be able to continuously learn in evolving environments. Let's say Michael has a best friend named Jack, and yesterday he went to the grocery store and met a new friend, Mary. Certainly, you want your AI to be able to recognize Mary without forgetting your old friend, Jack. And fourth, you want AI to be able to generalize across multiple domains and tasks. Let's say Michael was born in Singapore and he has never experienced the snow before. Last year, he traveled to Alaska with his AI. And the moment that they go to the airport and they see this cars and tables covered under the snow, usually Michael should expect the AI to still be able to recognize these objects. Last but not least, I want to say no one is born perfect, so is AI. In order to understand Michael's personal preferences, such as aesthetic taste, empathy, and love, this AI needs to constantly interact with Michael in order to augment its own cognition from social interactions. So to close these research gaps, my lab is drawing on neuroscience to develop a general framework for cognitive AI. And we mainly take two methodological approaches. First, we design and conduct human behavioral experiments, and we hope that these experiments would help us benchmark human and AI performance in several vision tasks. And these experiments would also help us identify research gaps and bootstrap modern AI. On the other hand, our lab is interested in developing computational AI models so that these models would help us further our understanding of human cognition. And hopefully these models would help us translate these insights to even further augment AI cognition. So these two concepts might seem very abstract to you right now. So now let me quickly flash several of my past works and hopefully to give you a sense of how we can apply these methodologies in specific examples. So here's a roadmap to cognitive AI. Given the time constraints today, I'm only going to cover visual attention, context reasoning, and So we all know that visual search is an ubiquitous challenge in our daily life. For example, you go to a party and you are looking for your friends in your party crowd. And here is another example of visual search task. In this task, the participant is sitting in front of the computer and trying to find where to localize where the calculator is on this complex search image. The red bounding box denotes the target ground truth location. And the yellow dots you see here is a recorded eye movement when the participant is looking for the calculator. We can see that the participant looks around and finally manage to find where the calculator is. We summarize 4 key characteristics for visual search. And although visual search seems effortless to you and me as humans, but I would say still a very challenging task for AI. most importantly, in the fourth property, we emphasize that humans are very good at zero-shot visual search. What I mean by that is, despite that this might be the first exposure of you seeing the novel objects, yet you have no problem in generalizing these concepts of novel objects and quickly localize this target objects. But if you think about right now the computer vision literature, right? A lot of people have been focusing on object detection algorithms in computer vision. I would say these algorithms deviate from human perception. And typically what these algorithms do is they exhaustively scan through the entire image using sliding windows, and then they predict a bunch of bounding boxes for every single object on the image, as well as their corresponding class labels. However, these algorithms often require intensive supervised training, and hence they fail to generalize to search for novel objects. Thus, inspired by anatomical connections in human brains, for example, here I'm showing this diagram of cortical circuits for vision in biological brains. And this is each individual boxes indicates the different brain areas. And we can see there are massive feed-forward and feedback connections. So inspired by these biological connections, we develop a zero-shot visual search model, and we found that our model approximates human search behaviors. So in order to assess the visual searchability for both computational models and humans, we designed 3 sets of psychophysics experiments, and we test them on object arrays, natural images, and water images. So same as the psychophysics experiments, our AI model takes the target image as the first input, and the ventral visual cortex is a 2D feed-forward convolution neural net. It extracts the latent representation of the target and stores it in the prefrontal cortex. Next, we present the search image to the model, and it used the same convolution neural nets to extract the feature maps of the search image. And then the pre-stored hidden representation in the prefrontal cortex can modulate these feature maps, generating a attention map. We can then take the consecutive maximum on this attention map to generate a sequence of eye fixations based on the principles of inhibition return and winner-take-all principle. So what is amazing here is that in the extended version of our model, we found that the model can even explain observations that have been puzzled cognitive scientists and neuroscientists for decades, such as this search asymmetry problem. So what do I mean by that? Well, so it just means that searching for the target A among distractors B sometimes can be more efficient than its reverse condition, that is searching for target B among distractors A. For example, what you are saying here is saying that the humans tend to find the targets under the vertical lighting conditions much faster than the horizontal lighting conditions. In this line of visual search studies, we summarize our key findings here. So we found that humans can search selectively, invariantly, and efficiently. And we introduce a zero-shot biologically plausible models for visual search, and we introduce eccentricity-dependent pooling layers in this model, and it approximates human search behaviors, even without any prior exposure to the stimuli or task-specific training. In other words, our model doesn't take any human fixations as the training signal, and yet it approximates human behaviors. So in the search asymmetry experiments, we found that this search asymmetry is a general effect to deep convolution neural net, and this search asymmetry behavior arises from the visual diodes that we input to the model. In visual search experiments, we realized that these models lack contextual knowledge. For example, the target here is to search for a toy windmill, while the humans look for the toy windmill most locations where this toy windmill is most likely to be, such as table surfaces. And you can see the model is typically looking for the toy windmill almost everywhere on the search image. And inspired by the recurrent connectivity in biological brains, we come up with computational models. And here we are interested in studying the role of context in visual recognition. So for example, what you are seeing here is a big chair misplaced in the parking lot. And if you fit this picture to 3 deep convolution neural nets, you realize that the probability for predicting this is a chair is less than 3% for majority of the deep convolution neural nets. Thus, we are interested in studying what, where, and how context modulates object recognition in both humans and the computational models. For example, given this, pointed by this yellow arrow, can you recognize that's a floating mug in the kitchen? We develop a biologically plausible computational models for object recognition that are aware of context, and we realize that our model shares a high resemblance with human recognition behaviors. It can recurrently deploy its attention iteratively across time steps and integrate contextual information. So here are several examples that we studied in context-aware object recognition, and we even violated some of the contextual rules here, such as gravity, and studied human and the model recognition. We launched the experiments on Amazon Mechanical Turk, and here is the experiment schematic. So after the first fixation for 500 milliseconds, the participants is shown with the bounding box indicating the target location. And then followed by this stimulus presentation for another 200 milliseconds under various contextual conditions. Then both the model and the humans are asked to type in a word to describe what they say in this red bounding box. So in this line of research, we found that the good context typically enhances recognition, while the wrong context hurts recognition. And a human visual system and the AI system seem to be relatively robust to low resolution contextual images, and they are also robust to various spatial configurations. This contextual modulation is a recurrent process, and it typically happens very fast, within 50 milliseconds. And we develop AI models that are aware of context during recognition. And we found these models share high resemblance with human behaviors under various contextual conditions, despite the fact that these models are not trained exhaustively on all the contextual variations. So here is a list of cognitive functions. And in neuroscience and cognitive science, people have intensively studied each of these individual cognitive functions. However, I would like to say in the AI community, we barely sketch the surfaces for some of these topics listed here, not to mention that these cognitive functions are often interrelated and functionally correlated. So far, we have covered the topics in visual attention and context reasoning. Right now in our group, we are looking at the working mechanism of continual learning and generalization with memory. In the future, we plan to study the working mechanism for social interaction, social intelligence in both biological brains and AI models. So it often takes a village to do research. And I'm very fortunate to work with these amazing people. And I'm definitely interested in collaborating with more people, talented people like you from RIKEN. Just to summarize, so I cannot emphasize more that despite all these advancements that we have made in AI, this AI models are still like cognitive mechanisms, and therefore we need to address those. To close these research gaps, my lab has conducted human behavior experiments, and I hope that we can seek inspirations from neuroscience and deploy those insights to develop smarter and more efficient AI systems. And I hope that one day with this cognitive AI framework, that these technologies would be able to empower the visually impaired person, such as Michael, to be able to see the world. So yeah, thank you. I'm happy to take questions.
Any questions or comments? Maybe I have a question.
Sure.
So currently, from the neuroscience side, so we try to understand our human brain, how it works. Do you think if when we develop AI now, neural network, even if it's inspired from our neurons, still many things are different. Do you think the future AI should more simulate our human, or learn something from how our human works to develop AI?
Yeah, that's a very interesting question. And so many, I think in the community, there are two parties right now. One is saying, I could just blindly doing engineering works and hopefully one day, I could just win the lottery tickets and find that amazing AI model that can perform everything, right? Another party is advocating to develop cognitive AI, that is to incorporate some of the human insights into machines. I would personally say that I'm not, I think both parties are right, and it's going to be exciting futures for both parties to explore together. But I would say given the current AI technologies, they are still lacking cognitive mechanisms. And I would say it's going to be a shortcut for us to first borrow insights from humans to say where we can develop, how far we can push in terms of cognitive AI. Then we can talk about superhuman intelligence after that.
Any other questions or comments?
What about the role of meta-learning in your model?
The
meta-learning. Zero-shot learning is one type of meta-learning.
Yeah, so here I don't have time to specifically go into the details. Basically, the idea here is that we want to borrow the knowledge that have been captured in object recognition tasks and transfer those knowledge to be able to help us to perform visual search. That is somewhat like a localization task, right? One is what, the other is where. So if you think about the brain, right, that there is a ventral and dorsal stream in the brain, in the visual cortex. And one is doing the what, that is recognizing what the object is. Another stream in the biological brain is doing the where question, that is where I can localize that object. So imagine that you have never seen this object before. I would say, as long as you are able to recognize that object, there shouldn't be any problems for you to localize that object if I throw it, in the real world, right? So I think somewhat this entire community in computer vision is studying separate these two problems individually, and they seem to be disjoint areas. But here we are trying to bridge the gap and saying that we can definitely transfer the knowledge from what stream to this where stream with zero shot. I hope that answers your question.
Hi, Dr. Zhang. Thanks for a great talk. I would like to ask, what the differences do you think the imitation learning and reinforcement learning with human in the loop, the relationship between this area with the area developed, the neuroscience, cognitive AI?
Yeah, I just want to first admit I'm not a typical expert in reinforcement learning, and I have definitely heard this brilliant idea about human in the loop reinforcement learning. I think it's something like incorporating the values, like what we want to AI reinforcement learning system so that AI can behave like us. I think that, yeah, that's definitely interesting area to explore further. Yeah.
Okay, thank you. Any more questions?
Let's thank the speaker again.
Thank you.
And we will move to the next one.
Hello everyone, this is Chen. I'm a postdoctoral researcher at Professor Sujiyama's team in our RIKEN AIP Center. I'm very glad to have this opportunity to share some our research on robust contrastive learning and its several applications. So before that, I would like to simply introduce our imperfect information learning team. Our research team is contained in the RIKEN AIP Center, and our team members have different research lines and several areas such as weakly supervised learning, adversarial learning, and self-supervised learning. But we have the only same goal, and that is to develop a reliable machine learning technique to deal with some those imperfect information or data in real-world applications. So in this talk, we would like to review some of our research achievements in the past 2 years that are related to my personal research areas, self-supervised learning, the contrastive learning. And we will discuss this topic from two parts that are methodology research and the corresponding application research. So self-supervised learning is a typical unsupervised learning case, and we aim to use critical prior knowledge to build some maybe pseudo supervision. And lots of recent work have already validated its very powerful performance, even compared with some semi-supervised learning or fully supervised learning approaches. We have done a series of work related to this self-supervised contrast learning topic, but I would like to select those 4 works of them in today's talk. Before this, let's just use 2 simple slides and briefly review the background and the problem setting of self-supervised contrast learning. The primary work of contrast learning is this instance discrimination technique published on NeurIPS 2014 and STAR-CFAR 2018. Actually, this is also a maybe negative sampling technique because it simply treats each pair of instances of training data as the negative pair. And the encoder network just learn an embedding to push away each pair of instances in the maybe feature space. And the very popular work SimClear proposed in SML 2020 further introduced the positive pair information, and they regard each instance and its data augmentation as a positive pair. So the learning algorithm just will pull in that instance in the feature space. When we further introduce both the negative pair and the positive pair data in the single loss function, we can obtain the very well-known influency loss, and this practice also showing very powerful effectiveness, even compared with some fully supervised approaches in different fine-tuning strategies. So contrast learning is also a pretty generic learning approach. It is based on the concept of pairwise similarity. So when we have the pairwise similarity metric for 2 input instances, we can directly do lots of downstream tasks such as classification, retrieval, or verification. And such a general purpose concept is also quite interesting and interpretable. As a early cognitive science research tells us, people not ask what is it, but people ask what is it like. This is a pretty interesting phenomenon. It means the human cognition tends to directly find out the similar points among the maybe real world things, and they may not really build some abstract concepts such as class or category. So from the real world application of the cognitive science viewpoint, we believe contrast learning is a quite general, effective, and also maybe interpretable problem setting. Now here we are going to the first part of our research on this topic. Our first work will consider a very simple and intuitive issue of contrast learning. As we know, in instance, the basic component, the instance discrimination technique will incorrectly push away some semantic similar examples. So this become a very common issue in contrast learning. Although some recent work proposed to use the rewriting or clustering technique to deal with this issue. The practical effectiveness of those methods maybe depend on the reliability of the learned feature itself. So we would like to investigate and address this issue from another novel viewpoint. This is a simple visualization experiment. So here we use the conventional CL framework to learn the feature embedding on CFAR 10 dataset, and then we obtain the corresponding histogram in figure A. When the class labels are available, within class and between class, distance obtained by metric learning can be discriminated with a margin region in the figure B. But we can find that the conventional CL algorithm are not good in this case because they fail to maintain a large margin in the distance space and for reliable distinguishment. So this just motivates us to convert the distance distribution property of machine learning to an unsupervised regularization term, so that we can further constrain the learning phase of contrastive learning. To this end, we remove the supervision from machine learning, and the only thing remaining is that so-called, I call it distance polarization. So to build this polarization regulator, we simply set two threshold data positive and data negative. We use the L0 norm to penalize and distance filtering into the region in data positive and data negative. And then we convert this L0 norm to the L1 norm for optimization. We also provide theoretical analysis to investigate the error bound influenced by the proposed regularization. We find that the error bound will shrink by the increase of the regularization parameter lambda. So it implies that our proposed this regularization is indeed very useful for improving the generalization ability of the contrastive algorithm. So here is some visualization experiment which can help us better understand the effectiveness of our method. This conventional method can only roughly separate data points from different classes. And in comparison, the projection results of our method are more distinguishable in maybe figures E and F. Then we would like to investigate another interesting issue in existing contrastive learning algorithm. As we know, the negative pair is a critical component of contrastive learning, which usually has a size of n squared. And this number of negative pair is significantly larger than those in fully supervised approaches. So we usually need the high dimensional feature to perform this instance discrimination goal. When the feature dimension increases, we can find that the training loss is indeed reduced. However, this also incurs an undesirable case where we find that this test loss is large. We can investigate this issue in a geometry viewpoint. When we calculate the volume of Hubble surface and Hubble cube in the h-dimensional space, we can find that their issue tend to be zero when the dimension increases. This phenomenon just tells us the data points in the high-dimensional space are very likely to be located in the corner of the Hubble cube rather than the central area of the Hubble cube. So, however, when we further calculate the corner number of the space, we can find that the number is significantly larger than our sample size. This is n hat and n. So it means for the high-dimensional feature, data points will very sparsely distributed in the space and will be far away from each other. We also have this theorem to reveal that the maximal distance and the minimal distance will tend to be the same and lose their discriminating ability for inter-class and intra-class. So to address this issue, we propose a low-dimension reconstruction-based method. We introduce a new projection layer in existing CL algorithm, and we use the new projection layer to reconstruct the high-dimensional feature in low-dimension random space. To achieve this goal, we built the L21 norm-based regularizer and obtain a sparse projection result. Finally, we can use this. We can obtain the low-dimension feature for fine-tuning or testing in the many downstream tasks. Here we have a lower bound for the max-min distance ratio, which provide a guarantee of the worst case of our method. And I think you can also observe this point from the two statistic figures in this slide. Here the red line indicates the lower bound of max-min distance ratios on different data sets, CFA10 and STL10. And then this is just a convergence analysis, since we use the stochastic gradient descent method to solve our density ratio problem. So we just needed to demonstrate the precondition of STD can be satisfied. So we have this theorem to reveal this convergence rate of our iteration algorithm, which is squared root t. So in our experiment, we firstly provide the ablation study to validate the accuracies on CFA and STL and can be improved with lower dimension setting. And here we also conduct a t-test to demonstrate the significant result. Then we observe from the histogram where this distance prediction become to be more accurate than the baseline method. So I believe this is why we can achieve better results on image classification than and so on task. Now we want to show some novel application case of the contrastive learning. One of them is the zero-shot learning, or called zero-shot recognition. In this task setting, we just want to recognize examples which have never seen before in the training data. And the common practice is to build an attribute-based predictor and recognize the main attribute of unseen class data, and then we can inference the class label by using the recognized attributes. But the existing method only consider the class-wise semantic descriptor, and they ignore the instance-wise divergence, which may limit their effectiveness for some important, such as fine-grained features. Contrastive learning is an excellent way to deal with this issue. So simply speaking, in the zero-shot recognition, all instances in the test phase belong to the unseen class, which is not involved in the training phase. But by using the contrast learning, we can still find out the similar instance and the corresponding attribute of the test data. Then we can perform the recognition task by predicting maybe the similarity between two instances and determine whether they're from the same class. And we have very nice experiments. The introducing of contrast learning block can significantly improve the recognition accuracy on both seen and unseen class data. One more thing is the cross-modal recognition. This is a pretty challenging task. For a visual clip and the corresponding audio clip, we need to give the specific area, which cause the audio frame. Suppose you have an audio clip and you need to tell us which is the location. And for this task, it is rather hard to provide the frame-to-frame annotation. So the self-supervised learning is used for the model training. People have already applied the idea of contrast learning to build the audio to visual data pair for model training. They usually assume the audio and visual clips from other videos are not semantically related. So they directly utilize the instance discrimination technique of contrast learning to push away different clips. But this practice would bring some false negative pairs when the audio frame and the visual frame are closely related. So suppose here we have 3 visual audio clips. The 3 boys are playing with guitar, and their audio clips should be highly close and related. But the common practice of audio to visual discrimination will push away them from each other. And this is not good for learning generalizable vision. So and the final visual localizing will also be affected by this. To solve this issue, we propose an active mining technique. In this work, we propose the construct several independent library M1 to MC, and each library MI will correspond to a specific semantic. So the examples in the same library can be taken as an anchor to describe its semantic. After that, we can extend the traditional NCE loss to an active set-based form. I think the main idea of this work share a very similar motivation of our ICML 2021 on dealing with the false negative data. But this work may should have much more practice details of domain knowledge in the cross-modal recognition. Here I show you some visualization results and the numerical results. A notable phenomenon is that when we increase the number of active contrast set and the number of semantic library, the recognition accuracies can be consistently improved by over 10% points. And I think this result clearly validates our motivation and emphasize the significance of using our active set mining technique for this challenge, cross-modal data. I just find that Dr. Xiaoyu will also give a talk about the application of self-supervised learning in the cross-modal topic. So let's also look forward to her talk in this afternoon. So in future, we could further consider some other interesting topics, such as the similarity organistic concept. For example, we have two-board example image, and they are regarded as dissimilar pairs under the homology reference, but they can also be regarded as a similar pair under the heterology reference. This is a pretty interesting phenomenon. I think this may motivate us to build some more plentiful self-supervisory information for model training. And we are also trying to develop some novel applications of contrast learning for the fundamental science, such as the molecule property prediction, where we convert the molecule data into a graph and use some graph contrast learning technique to deal with it. And this is just our some ongoing works. Okay, this is the end of my talk. Thanks a lot to my supervisor, my mentor, and my excellent colleagues. All right, thank you for your attention.
Hi, sure. Thanks for your great talk. I believe contrastive learning is a very important technique to have a very good embedding and pre-trained model, which is a fundamental technology for the ChatGPT plus region transformer. I just want to know your opinion. Do you think is there some more applications leveraging the pre-trained model? What do you think? Some more applications.
I think it's a pretty good question. Yeah. Currently, the pre-training model are mainly applied in the cognitive problems such as classification, retrieval class. Maybe in the next step, some fundamental science may need some more. I think the pre-training technique can be used in many fundamental science, such as I discussed in this slide.
Yes.
Yeah. So this would be very interesting. Area. Yeah.
Sorry, I have another question. It's a little bit technical. So right now, the pre-training require a large amount of data. So do you think it's possible to reduce the amount of data for the contrastive learning?
Yes, that's a great question. Actually, we are aiming to do this target in last year. Maybe some sampling selection technique can be used to select some important examples or instances from the training data, and we can just learn from those instances to train a reliable maybe representation network. Yeah.
I see. Thank you.
Okay, thank you.
Any question?
Thanks for a nice talk. So I have a question, two questions. One question.
Thank you.
So in your experience, how important is the role of the difference of augmentation involved in getting a contrastive learning to work? That's the first question. Second question is beyond the visual domain. So we are interested in things like time series and other forms of data. So what's your opinion on contrastive learning for these other domains? Thanks.
Sorry, can you repeat your first?
Yeah. So what is your opinion? How important is it for the different sort of augmentations that you use, right, for the contrastive learning to work when you do your positive pair versus negative pair, right? How do you need to do like some data augmentation, or you need to do some way to select the positive versus negative pair, right? So how important do you think that is for you that?
Oh, I think the two things are both important, and they are from the different angles, and but they have the same target to improve the reliability and accuracies of the learned representations. I think it is pretty hard to say which one is more important. So maybe in some popular work, the positive pair mining has dominant trait, such as the Dino or UIOL, and so yeah, they have obtained significant accuracies than just using negative data. Yeah.
Okay, next, then maybe about the second question. Have you explored contrastive learning beyond images? And what is your
beyond image? Sorry.
Yeah, beyond image data, right? Yeah.
Beyond image.
So like time series or like
audio. Yeah.
Text, yeah.
In my work, I didn't do this experiment, but the contrast learning has already used in this problem and the time series data such as CMC or some audio-based recognition tasks. Maybe this work is a time series based task. You have some audio series and the visual series, and you use the contrast learning to deal with them.
Yeah. Okay, cool. Thanks.
Okay, thank you.
One question here. So in contrastive learning, it actually depends on the choice of negative samples. So usually the positive sample is very few, and we have abundance of negative samples. So in this case, you may introduce a lot of bias from the negative samples. In your case, how can you handle such kind of imbalances between the positive sample and negative samples?
The balance, actually, my work is focused on the focus on just the negative samples, but I think the two things are not contradictory. So. Yeah. Maybe we can talk about this by email. Yeah.
Thank the speaker again.
Okay, thank you.
Hi everyone. So I'm Sheng. I also go by CS. So I am an investigator at STAR-CFAR, and I also lead a group focusing on data efficient deep learning at the Institute for Infocom Research. But today I'll be giving a talk on my work at STAR related to resilient and safe AI. So the title of the talk is Fourier Perspective on Robustness, and it will be just focusing on one work. I hope it will be of interest to you guys. So first, I'd like to motivate this work by asking the question, why do we want to adopt the Fourier perspective to robustness, right? So I think this is sort of motivated from the perspective of some of the real-world corruptions that we look at when we work on our projects with, say, industry partners. So for instance, things like various sorts of noise or blur that may occur in real life. This can be viewed from the Fourier frequency space as shifts in the sort of the frequency spectra or the amplitude spectra in the Fourier space, right? So this is one of the motivations. And I guess the other motivation that we sort of drew was from some of the work that's done here and at the University of Tokyo on the relationship between Fourier perspective and the adversarial and examples, right? So specifically, this work provided some theoretical analysis looking at the structural sensitivity of linear convolution deep networks in sort of various Fourier basis directions, right? So basically, you can find specific Fourier perturbations that are input agnostic, and basically it means that you look at let's say this bird, right, is a bird, but like when you add on this adversarial Fourier pattern, it will change it into an image that still looks like a bird, but it will get incorrectly classified by a CNN. And this perturbation is actually input agnostic. So it's a sort of a universal adversarial perturbation, which makes it quite dangerous, right? So these are the sort of the two key reasons why we decided to look at robustness from this Fourier perspective. So I guess in this one work, we made a few contributions. And the key one is to how do we define this notion of sensitivity to Fourier basis directions, right? And we have a way to do it without having to explicitly convert your input into Fourier space and then computing this sensitivity metric. And once we have this sensitivity metric, we can use it to define a regularizer to basically control the inductive bias of the network, to adjust the sort of sensitivity of the network to different Fourier frequencies. And that can help it be more robust to certain types of perturbations. So first I'll talk about briefly the sort of small mathematical observation that we had that allow us to do this, right? So first of all, one way you can compute this sensitivity to various Fourier directions is by first converting your input into Fourier space, and then after that, you train a network on this Fourier representation, and then you compute the gradient of the loss with respect to the input, and that's the sort of sensitivity of your model to various Fourier directions. But then that requires you to sort of build your model in the Fourier space. But we are saying that, okay, actually, because the Fourier transform is a unitary transform, so it has this nice property that the inverse is actually the adjoint, which means that when you do the chain rule, basically we can simply train the model in the original input image space, compute that gradient of the loss with respect to the input in the original input space, and then just perform the Fourier transform on that gradient, and you will get the same result as if you did the whole thing in Fourier space at the beginning. So I mean, this sort of applies to other transforms like wavelet and stuff, but we in this work we focus on the Fourier transform. I mean, like if any of you have other interests in looking at other sorts of transforms or like providing some more mathematical analysis, we will be happy to collaborate on that. So using this result, we basically can define a measure of Fourier sensitivity. So how do we do this? This slide shows the picture of how you compute what we call the Fourier sensitivity of a model. So on the left side is the input image, and then we compute the gradient of the loss with respect to the input. So you get this sort of like a saliency map, right, that people have used for interpretability. And then you can compute the discrete Fourier transform of this input gradient, and you get that picture in the middle, which shows you the various sort of like, this is the amplitude spectra, the power spectra, right? And then and then we define sort of different rings of frequencies, right? So different radius from the middle. The middle is the what we call the DC component, so like the average value of the image across the whole data set, right? And then you look at the various sort of frequency, which is the radius around the middle, and we sum up the amplitude of the coefficients within that frequency band, right? So we can generate a histogram based on these powers that are summed up in the different rings, right, around the middle. And that histogram, that vector of values, basically the ratio of that power in that one ring to the power in the entire sort of circle will be the sensitivity at a specific frequency. So this whole vector that we define there is what we call that Fourier sensitivity. So having defined this, we start looking at how does this Fourier sensitivity look like in different networks, and how, depending on how you train them. So here we first look at the effect of Fourier sensitivity on different data sets. On the left side is ImageNet, in the middle is CFAR 10 and SVHN. You see that so the first line you should look at is the green line, which is the standard training model. You just train it normally, like minimizing the cross entropy loss. And you see that there's a slight shifts in the different Fourier sensitivity characteristics of the model depending on the data set. The blue line is showing, okay, when you do adversarial training, how does that affect the sensitivity of the model to different frequencies? And it actually shifts it. Oh, sorry, the blue line is standard training. The green line is the adversarial training. So the adversarial training shifts the sensitivity to the lower frequencies. So in some sense, it's like, you know, your model is more resistant or ignores the high frequency components in the image, which tend to be like the noisy parts, right? So that's kind of agrees with your intuition of what adversarial training might do. And so it also depends a bit on the architecture, although it's not so evident, I would say. So on the left side, we have some of the more recent transformer models, and the right side is mainly the convolutional type models. And you know, they are usually this is on ImageNet, they are usually sort of sensitive to the mid-range frequencies. But there's some slight variation depending on the specific model type, but you know, for the most part, they are sensitive to the middle range frequency trend. And then if you look at the sensitivity of adversarial attacks, right? Basically, you know, there's some debate in the community about, are these adversarial attacks low frequency phenomena or high frequency phenomena? And what we see is that if you look at you compare the frequency, the Fourier sensitivity basically of the attack to the Fourier sensitivity of the model, they actually align quite well. So you know, a baseline model that's just trained normally, the one that is the one that looks like a Gaussian, that you know, if you train it normally, then the adversarial attack also has a similar sort of Fourier sensitivity spectrum. If you train it adversarially trained, then the adversarial examples on the adversarially trained model will also have a similar spectrum. So I mean, like, this is in some sense to be expected, because some of the attacks that we use, like PGD, these are essentially computing the gradient with respect to loss, right? Trying to increase it. So there's some relationship there, right? Yeah. So now, you know, having sort of defined the sensitivity and looking at what it looks like for various models. So we have to devise a way to modify the sensitivity of a model, right? So that we can sort of affect its behavior and make it more robust to certain types of perturbation. So one thing that we did, I mean, this is one way you can do it. It's a simple way, and there are more sophisticated ways you can do it, but this is a first sort of attempt. Is that, you know, we can simply say, okay, we want to minimize the sensitivity to various frequencies by implementing a regularization term. So for instance, so let's say we wanted to make the model more sensitive to low spatial frequencies, right? So these correspond to basically the green circle, like the parts of the DFT spectrum in the green circle. So we basically say we want to penalize any sensitivity outside this middle green circle. So like in the yellow circle, in the red circle, and everything like that. Similarly, you know, if you want to make your model sensitive to more mid-range frequencies, you can, you know, just penalize the power in the green and the yellow circles, and so on and so forth. So for the last one, where we want to say, okay, we want it to be sort of evenly distributed, we basically try to maximize we try to try to maximize the entropy, right? So we just try to encourage the model's sensitivity to be evenly spread out across the whole thing. So, you know, this loss or regularization term is differentiable, because it's, you know, you can easily just compute it, and it's differentiable, and we can just add it on to your usual cross entropy loss or whatever task loss you want, and train your model. So these plots here, they show that, okay, the blue line again is the original model. The green line is the one where we encourage the model to be sensitive to more low frequencies. And you see that the frequency, Fourier sensitivity gets shifted appropriately towards the lower frequency. And similarly, for the red line, it's the medium frequency sensitivity. So the Fourier sensitivity gets shifted to the middle, and similarly for the high sensitivity regularizer, it actually shifts the sensitivity to the high end, right? And then for the ASF, which stands for all spatial frequencies, it kind of distributes that sensitivity across the entire range of spatial frequencies. So this shows you that the regularizer does what we think it is going to do, right? So now, what is this useful for? So first of all, we did this experiment to show that the regularizer can help us bias the model to learn more global features rather than local features. And how do we test this? So what we do is we take the image, we basically divide it into a grid, and then we shuffle the different patches, right? So this basically removes the global structure in the image. And if your classifier is still able to do well, that means that it's using the local features to make a classification. So basically, what we want to see here is that the more your model is using global features, the more its performance should drop in this experiment when we use patch shuffling, because the global structure gets disrupted, right? So here you see, like, for instance, for STAR-CFAR 10 with the standard training model, the accuracy is 66.5, right? But then when we sort of bias the model towards lower spatial frequencies, the performance drops by quite a bit, and it drops the most with respect to the others, right? Which means that it tends to use more global features rather than local features to do the classification. And this can be a desirable thing if you want it to not be so sensitive to sort of local perturbations, like patch-based adversarial attacks and things like that. So that's the first experiment. The other experiment we did here is, can it also confer robustness to sort of these Fourier noise perturbations that we talked about a bit in the beginning, right? So here we can artificially sort of inject noise into the images by limiting, basically doing a bandpass filter, right? So this left column here shows you the mask that we use, right? So the white part means that we let the frequencies in that white part through, and then the black part get removed. And as you can see, the more we restrict it, right, to lower frequencies, the more blurry the image gets as you go down the rows. And what we can show is that if we appropriately regularize the model with the correct sort of regularizer, so that we encourage the model to only use those features in those appropriate frequencies, then the model will still be able to perform well, even though the image is severely degraded. So that's what we show here. Whereas if you look at the other sort of standard trained models, the performance drops a lot as you increase the sort of you sort of limit the frequency range of the input. So my last slide here. So this goes back to the original first picture that we showed on the real sort of out of distribution shifts, right? So here we're looking at how do these regularizers perform in the presence of these real out of distribution shifts, like short noise, Gaussian blur, various sort of weather conditions like snow, fog, and frost, things like that. And what we show here is that there are actually specific types of regularizers that you might want to use in order to make your model more robust to different types of perturbations, right? So for instance, on the left side, when you look at the various sort of blurs, the low frequency sensitivity models, the LSF models, basically they perform the best because you encourage the model to you make use of the low frequency information, which still remains, even though when you do blur, you basically remove all the high frequency information image. So by encouraging your model to use the low frequency information, then you will be able to perform much better than the rest. And then there are also some other potentially interesting observations here, is that for the sort of weather perturbations like snow, frost, fog, or like brightness variations, actually it's the ASF regularizer somewhere at the bottom that performs the best, which means that you don't really want to limit it to a specific frequency sensitivity, but by encouraging it to be sensitive to a broad range of frequencies, it does better. Yeah, so I think that's all the results. And in the future, I mean, we are going to try to extend this to other data modalities, because Fourier analysis is very natural for other things like time series, audio, and even potentially graph data, and also for other tasks beyond classification. And I think if we are able to more develop a deeper understanding of when this will work well, or when it would, for instance, using more formal methods to characterize the method, I think we would be quite interested in that. So yeah, this work was recently published in TMLR, and if you are interested, I'm happy to take any questions. Thank you.
Hi, Dr. Fu.
Yeah.
Thanks for your good talk. I have a question on the network structure you use.
Yeah.
Basically, you conduct experiment on convolutional based networks.
Yeah.
So therefore, this phenomenon could happen. But for example, for the transformer-based networks,
Yeah.
for the attention-based networks,
Yeah.
do you think Fourier sensitivity analysis also works in, for example, the vision transformer or the T?
Right. So I mean, we did do some, we did look at the sensitivity to different sort of transformer networks here on the left side, right? The blue and green lines. I mean, the green line with the sort of the bump at the end. So they do have a interesting sensitivity as well. And I think, you know, it's not sort of, I mean, you can always look at it, right? The question is whether it's going to, and we can always modify it. So I think in some sense that answers your question. Yeah, we can always look at it and we can always modify it because we are just looking at the sort of input gradient, right? And it doesn't matter what model you use, you will always have some sensitive direction.
Yeah, so I'm wondering whether the sensitivity direction align with the convolutional neural, for example, vision transformer.
So from this plot, it's not exactly the same. Yeah, because you see the pattern is a bit different. Yeah.
Just give me the feeling.
Yeah.
They have some long tail.
Yeah, they have some different pattern. Yes, it's a bit different. Yeah.
Yeah. Okay. Then we can need another tricks afterwards. Series data source of using transformer.
Yeah.
Okay.
Thank you. Yeah.
Thank you for the great talk. So I just want to make a comment. So I'm not sure whether this could be connected somehow. So in the kernel methods, I guess it's a pocket machine, for example, we have the norm regularization, that is just norm regularization.
Yes.
It has a very clear, very explicit Fourier regularization interpretation. So the functions with, like for example, for the Gaussian kernel, for the Laplacian kernel, we have a very clear and very Fourier regularization norm. Actually, the norm is actually expressed as a Fourier norm, basically. And so it has a very clear Fourier regularization interpretation. So the functions with high frequency will be penalized. So the functions that we have are really penalized. So it kind of the models that prefers functions which are smooth, low frequencies. So I'm not quite sure whether it might be connected to this setting. It's possible. I don't know.
I mean, I think we should discuss this.
Yes.
Yeah. Maybe we can have some result for like single layer network, right, which is equivalent to some sort of kernel.
Yeah, it could be interesting.
Yes.
It could be interesting.
Yes.
Thanks a lot.
Thank you. Yeah.
Thank you for your great talk. I have a question about, in your slide, you say Fourier regularization enables bias towards global features. Okay.
Yeah.
Are there any reasons?
Are there any reasons? Okay, let's see. Yeah. So I think one way to think about it is this, right? So I think the high frequency parts, right, they tend to be changing more frequently. So in some sense, it's more local, right? Rather than low frequencies, which is more, you know, the scale is a bit larger. So in some sense, when we bias it towards the lower frequencies, you encourage it to look more at these more global features in that sense. Yes.
Okay, my next question is, can this be changed when we use the wavelet transform?
Yeah, so we haven't looked at wavelet. If you are interested, we would definitely be interested in just talking. Yeah.
The wavelet is more localized.
Correct. Yeah.
Thank you.
Yeah.
Any question? Yeah, I have a question about.
Yeah.
So do you think your regulator can be attacked in the future again?
Attack?
Because
course.
any method, if you develop some
course.
attack coming again.
Yes. I think it can be attacked, right? So I mean, in some sense, that's what we are saying. This one, right? So we are saying that, okay, yeah, you train, right? You train a model, you train it adversarially. you will still be sensitive to certain directions, and then you can be attacked in the directions, right? So I think the question for us is, in a real world setting, usually you don't have access to the model. So I don't know whether by let's say we do all frequency sensitivity, then it may be harder to find a specific direction to attack. I wouldn't say it's impossible. I mean, you can always find a direction to attack. Yeah.
For example, you encourage low frequency in the global feature.
Yeah.
So in the future, attacker may learn the perturbation which must be low frequency.
Yeah.
It's more difficult to attack.
But it's more difficult, right? Because if you remove too much information, then basically even the human cannot understand what the image is, right? And then at that point, is it really an attack? The label will change everything. So thank you.
Any other questions?
Thank you very much for your talk, for very insightful. Just follow-up question for you about the ability of attacking such new mechanisms or defenses. Generally, because as you mentioned, in the real world, we don't have really access to models, etc.
Right.
Did you check whether your defense properties generalize to black box attacks or
so this is something we haven't looked at, and we are going to look at it in a future project. Okay. But if you are interested, again, we should talk about it. Yeah.
Sure.
Yeah.
Thanks.
Okay. All right. Let's thank the speaker again.
All right. Thank you. Yeah. Very good afternoon to everyone. My name is Hwee. I'm going to give a talk on artificial gender intelligence. I'm the PI of STAR-CFAR, and I'm also taking care of Department of Artificial Intelligence at the Institute for Infocom Research, and also co-director for this Joy Lab with France called IPEL, CNRS, A-STAR, and NUS. Okay, the talk I'm going to share today, the title is AGI, Challenges and Opportunities. It's not going to be very technical per se as go into particular detail. I'm more trying to stimulate some of the thinking by looking back, looking forward, and this is the exciting area and we are all looking at doing AI, and AI is moving so fast. In fact, some of the material I prepared is like before GPT-4 was announced. So we probably have not really understand what GPT-4 can do, right? What is missing? It's still like a black box. So what should we do moving forward? Okay, so this is the plan. I'm going to just give a very quick historical account of what happened in the area of AGI or intelligence in general, and then talk about types of evaluation paradigms and so on, and then what is still missing, and then hence what is the desirata, what we hope to have, what we think we should have. And then I can also share some relevant works at STAR-CFAR, but more to advertise what we have been doing related to this area. And then, of course, my personal interest is to connect this to brain science to have more inspirations. Okay, so first let's look into the history. Right. So what is AGI? If you look at from the web Wikipedia, it says it is the ability of this intelligent agent to understand or learn any intellectual task that human or animal can do. Okay, it's also so-called the strong AI, and versus the so-called the weak and narrow AI. So a mathematical precise specification has been done in the beginning by this Marcus Harter in year 2000. So his approach is very mathematical, try to formalize something, in fact, like a optimization problem, maximize the ability to satisfy certain goals in a wide range of environments. There are also other approaches. Anyway, this term is sort of popularized by these two guys, Sheng and Ben Gordell, and around about 20 years ago, and they actually have a first book in 2006 to collect all these papers around this area. And there's a conference on it also. So I mean, if people who are interested to follow this trend, you can go to this website to get all the information. And we all know that just last year, DeepMind developed this Gato,
which is a general purpose agent that can do 600 over tasks. And of course, it is not able to do everything at the state of the art. Some of them are, above average. And now with ChatGPT, I think this is considered not as a state of the art anymore. But essentially, it is a multimedia transformer that can perform tasks, as you can see listed there. Now we have also a lot of effort in generative AI, the large language model or multimedia language model like GPT-4 and so on. And of course, Google has their own version, Baidu, Stanford, all this. So essentially, the take-home message here is that solely measuring skill at any given task, short of measuring the intelligence, it can be, as long as you have enough prior knowledge or enough training data, you can actually sort of buy this arbitrary level of performance. Okay, so is this intelligence? Okay, so just switch to a different topic here, in a sense that there's a recent survey last year, actually asking researchers in this area about, they contacted about 4,002 researchers, and then about 70% responded. Basically, the main result they asked is that we have high-level machine intelligence. Let me see. Okay, so the idea is that 50% chance of getting this high-level machine intelligence will be done in 37 years. Okay, so this is the so-called people's confidence. However, that's before GPT-4 and ChatGPT. Okay, so now maybe people will feel even more gung-ho and think that it will be coming faster. Yeah. Okay, so just a bit of history. Until 2007, there's no very systematic general survey or test to talk about this definition about intelligence. Okay, so if we were to take this definition as intelligent measures an agent's ability to achieve goals in wide range of environment, then there are two aspects. One is the task-specific skills to achieve the goals for different skills, requiring different skills. And then there's also the aspect of generality and adaptation in a wide range of environments. Okay. So the first school of thought is that we just treat intelligence as a collection of task-specific skills. Okay. So this is actually the way that our pioneer in AI, Marvin Minsky, has defined in 1968. So AI is basically a science of making machines capable of performing these tasks that would sort of require intelligence if it's done by human. Okay, but the problem is that it never says exactly how this can be done, and in terms of evaluation, right? There are different approaches so far. One is the white box analysis, but this only works if you have a very precise, well-defined task and environment, so that you can actually illuminate all kinds of input-output responses. Then you test the system using this input and test the output, just like our testing cases for algorithms, right? However, AI is more open-ended. So another way is use human review like Turing tests. So someone interact with the agent and try to understand and try to decide whether this is considered human or not. And this is very subjective. Okay. And of course, the other way is human compete with the machine, like AlphaGo, like chess player. And then we all know that in this case, the machine has defeated the human. And of course, nowadays we have lots of benchmark. I think for people doing PhD, it's very tiring. Every time you need to publish a paper, you need to do many kind of benchmark. And more interestingly, nowadays, with the ChatGPT, able to pass all the important exams for medical school, law school, and so on. This is like even on par with human intelligent capabilities. Okay, so in this paradigm, intelligence is a collection of task-specific skills, like chess and Go and so on. But there's no clear path from how specific, how to go to general. Okay. Right. Then John McCarthy come along, the father of AI, who coined this term AI in the DARPA workshop, right? And in '87, he started to look at AI is the science and engineering of making machines do things that they have never seen. They have never seen and have not been prepared beforehand. So it's our so-called the generalization capabilities. Okay. But again, if you talk at generation in different specific skills, then it is still not the general enough. Okay, so here we want the intelligence to be able to acquire new skills through learning. And then this ability can be directed to a wide range of unseen contexts. Okay. And of course, we have been talking about all these, out of distribution, generalization, and so on. As you can see that there are different levels of generalization. Okay, so this is where the machine learning, deep learning become hot again. But you can see that a lot of research has been targeting at how to make these generalization capabilities. Yeah, in fact, you can look at deep learning as a kind of very locality sensitive hash table, right? Nothing, smart in terms of doing just hashing. Okay, so people from the psychometrics, okay, psychometrics is the theory and techniques of measurement of these psychological constructs, including intelligence or even other kind of mental construct state, depression. Okay. So for them, they have defined human intelligence with two important aspects. One is the fluid intelligence, which is that flexibility when you see certain pattern, you are able to generalize to unknown patterns. Okay, and this will require very little on prior knowledge and learning. So very typically those IQ tests that we do in the during the test, you see few patterns and you try to look at what is the next one. Then there's crystallized intelligence, which is very heavily based on what we have learned. For example, language, arithmetic, and so on. So this actually reflect experience and knowledge. And hence, some people who sit for IQ tests, they can actually drill to score very well, because if their vocabulary is good, and the arithmetic is well practiced. Okay, so key takeaway here is that there are still a lot of things unsolved. First, we should be measuring the abilities, not the skills. Okay, and then how to quantify these abilities, and then the tasks, how to design such as they are unknown, okay, to the test taker. And of course, there are other issues like reliability, validity, and so on. Okay. So now I'm going to switch to what is missing and what is desired. Okay. Right, I'm going to use this recent work, as you can see the citation below. Basically, this is targeting at this large language model in particular, like ChatGPT. So there is a misconception that if you are good at language, you're actually good at thinking, good at thought, and vice versa. And in fact, Turing test is something like this. So if you interact with, an agent, and as if that he can reply you with all the nice, structured, well-formed languages, sentences, and you think that, hey, this guy is thinking and telling you the right things. Okay. However, if you look at it carefully, as these authors try to explain, there are actually two kinds of competencies. One is the formal linguistic competency, where all these ChatGPT is demonstrating, and the so-called NLP people, the systems. Okay, so this is defined as a set of core specific capacities that is required to produce and comprehend a given language. And interestingly, if you look at the brain region, there's actually a set of regions interconnected in the frontal and temporal lobes, okay, the left-hand side in particular, support this comprehension and generation of language, okay, whether it's spoken, written, and signed. Okay, but it does not support other kind of condition. Okay, as you can see listed there, for example, you are engaging in logical reasoning, arithmetics, even writing computer program, listen to music. This part of the brain doesn't get activated too much. Okay, they require other aspect. So what is missing? So the author actually listed 4 areas. The functional linguistic competence. These are actually, and they show that there are different brain regions that correspond to these activities. So when you do formal reasoning, you try to do even is mathematical or physical reasoning, logical inference. They actually activates a different set of brain regions that are quite distinct from the language network. Okay, so immediately you know that the brain itself is not using just language to solve logical inference. And also the knowledge about the world, the common sense knowledge, again, it is a different brain region. In fact, the semantic knowledge, if people who have this neurodegenerative disorder affecting these primary anterior temporal lobes, they will have problem with the world knowledge. Okay, for example, they cannot tell that a zebra has stripes. Okay, of course, language-wise they can still put this, but they actually cannot tell the meaning of that. And the other one is situation modeling, which is embodiment, right? It is defined as the mental model of entities and relations between them, and a sequence of states that they need to track in a longer context and integrate with linguistic and non-linguistic information. Okay, so for example, when you're watching I call that a drama, you are able to understand after maybe 10 episodes, you're able to recall what happened in the first episode, second episode, all the relationships over a long durations. Of course, we don't know, maybe ChatGPT can do something now better, okay? But again, this is still not a solved problem. And of course, social reasoning, the process of inferring the intended meaning of the utterance beyond the literal content, this is again a different set of brain region, the theory of mind network. Okay. So in conclusion, real life language is very different from just that kind of just purely linguistic. It is fundamentally embodied and social. Okay, and we need to integrate language into a broader cognitive framework. Right. So I mean, in my opinion, I feel that there are at least 4 areas that we can look into to have this future of AI. Of course, some of these are already in the research, like domain adaptation, transfer learning, and in the science of learning for human is actually called learning transfer. So someone who have learned a particular skill, able to transfer this quickly to another domain. For example, near transfer and far transfer. For example, you learn how to drive a car. When you go to a different country, you rent a car. The car model may be very different, but you are able to transfer it rather quickly. But then if you are asked you to go and operate an aeroplane, then you need a lot more adaptation, right? Or you need new skills. So this is really from what you have seen before, the past and the context to a different one. Is what is happening in the external environment. Then there's also the issue of grounding, which is what embodied AI tries to address. And of course, this issue of variable binding, where in our brain is doing this variable binding. Okay, so this is about how information perception from environment to go into our internal representation. And in terms of internal representation, how we represent parts to whole and vice versa. This is the issue of composition, representation, and similarity. Okay. This Paul Smolensky has been pushing this area called neurocompositional representation. I think it's worth taking a look as well. And of course, now everybody is going for large language model, larger and larger, from 1.75 billion to I think 150 billion. And I don't know how much is GPT-4 now. Okay. So basically the idea is that as long as you have enough data, you have enough computation power, you can build a gigantic model to have everything inside. But is this the way the brain operating? I believe not, right? So we actually have a modular architecture, and we have a way to organize and control this information flow when we solve a task. Okay, so be it a competition or collaboration among the different brain regions. Okay, so I'm going to quickly skip through certain work in STAR-CFAR, which we have started effort in this area. Okay, for example, we have participated in this Epic Kitchen 100 unsupervised domain adaptation. So the goal here is to adapt one action recognition model trained on label source domain to unlabeled source. So in particular, this data set allowed us to do so. They captured a lot of video in first-person egocentric view, which is quite challenging, because as you can see that when we move our head and so on, the things are moving. Okay, so there are many different kind of kitchens in different cities, and there are also multi-language narration, different 90,000 action segments, and so on. Okay, essentially there are 97 verb classes, action class, and 300 noun classes. Okay, so you are supposed to recognize the action and the object, the noun. So we participated 2 years, and we got the first ranking for this category of action recognition for unsupervised domain adaptation. Okay, so in the first year, we studied the data set. We realized that the presence of distracting objects is challenging, because there are a lot of cluttered objects in the kitchen, and some of them and the actions sometimes look similar, with the hand movement. Okay. But we make observation, and we realize that the objects are usually the most important objects are located around hand. So obviously we need to have hand as our main focus. Okay. So we have designed hand-centric features to reduce this abstraction, to facilitate this domain invariant learning. Okay. Yeah. So we basically add the hand detectors and use it to enhance the features to be more discriminative. Okay. Right. So I think for that we are able to push the performance to the top. I think now the state of art is about 30%, but as you can see that this is still a very unsolved problem. Even just to able to adapt to a different environment, just very constrained actions and objects is already very challenging. If you're talking about AGI able to adapt to any kind of environment, any kind of activities, that will be even more challenging. Okay, then last year, we realized that the method is still limited. We observed that if we directly just align the source target features, you will introduce this extra noise and reduce the discriminativity. Okay, and so our solution is to put in this action-aware knowledge in order to increase the discriminativity. And we also have a small module that is look at this co-occurrence of verb and noun to further filter and improve the action prediction. Okay, so essentially, the left-hand side on your left is basically the pipeline of using CNN to extract the features, and then after that you use a graph convolution network to encode them. But the differentiating factor is on the right is that we have classifier that is actually to classify the actions, and this knowledge encoded in the weights are used to so-called filter or clean up the features that we learn before we do the alignment with the target domain. Okay, and then we use a simple co-occurrence matrix to sort of filter out the noise, unlikely pairing of verb and mouse. So we push the performance higher to close to 25, still at the top. Yeah, I guess the state of art is still far from practical. Right, so next I'm going to quickly just run through some of the other people's work in the STAR-CFAR. Another PI who is working on embodied and cognitive AI is not able to hear, so he just want me to help to flash his work. I mean, you can scan the QR code and you can get all his papers. Essentially, he's working in embodied AI, looking at how to use so-called mental simulation to predict future frames. And then from there, they have invented or modified something from NLP, from span predict to span selection, using the salient features to look at the what is more likely to be the future actions. Okay, so they have a data set that is able to combine this current data set together and get the best performance. Okay, and they are published in all the recent conferences last year. Another work which is just published as an oral paper in this year's AI is to look at this counterfactual dynamic forecasting. Again, it's related to the previous one, but on instead of physics AI, talking about causal reasoning and so on. Yeah. So the idea here is to formulate a different problem, which is different from the state of the art. Okay. We tackle three types of problems. For example, the type 1 is called the counterfactuals with respect to the human imagination of what's going to happen. For example, to answer the question, what will happen if the cup is moved toward to the edge of the table? So this is to predict what happened if something is continued to allowed to continue. Another type is how can we avoid sliding if the plastic was replaced? So it's like, imagine something is replaced by something change, some attribute change to the current state. So what will happen? The third one is quite different. It's basically saying that if something is removed or something doesn't happen, okay, what will be the outcome? Okay, so I won't go through the details. So essentially, we use some toy problem. Left-hand side is the point mass, and then the right-hand side is a chain pendulum. So basically, we look at what happened next, like whether there's a collision with each other, the balls, or with the wall, and what if one ball becomes bigger, the size, the mass essentially, and what if one ball is removed, and see what's the outcome. Okay, so the last part of my talk will be connection to the brain science. Okay, so I'm particularly interested in this area of the brain called prefrontal cortex here, because in terms of structures, it is very interesting that the prefrontal cortex actually receive projection from all the sensory input, the visual, auditory, and so even if it's not direct, it's also connected to a region that is then connected to the raw inputs. So it's actually have a convergence of inputs from all the different modalities. Okay, and then on the other hand, in terms of output, right, it actually affects not directly to the primary motor cortex, but he has extensive with premotor areas. which then in turn have projection to primary motor cortex and the spinal cord. Okay, and you can also neuroscientists show us that it has also done interconnection with basal ganglia, which is automated behaviors. And not only that, it also have connection with our memory, episodic memory, our other cortex, and then the emotion control center, and so on. And within itself, it's also interconnected densely, and then it has feedback to this region beside receiving input from them. So what does it mean? So it has these following functions. One typical test is this. People, neuroscientists have done is that, for example, you are asked a task to look at a word. Say the word is blue. The word is blue, but it's written in red, right? So you're asked to, given the word, either you read the semantic blue or you actually read out the color of the word. So you can see that when we have two perceptual input, the color and the text, one is maybe visual, one is language. Our brain is competing, but you must have a way to actually suppress one path and allow the other one to be the winner. Okay, so first, this working memory has to have an active maintenance of these packets of activities. And then you must be able to provide these bias signals throughout and guide this flow of activity to establish the proper mapping between from the input, the internal state, and to the output. Okay, and especially when the stimulus are ambiguous or even competing, then among these multiple responses, what is the given current task or current goal that you require to satisfy and compete with a stronger alternative? Okay, so this is like representation of a kind of template, the rules and goals. Okay, so these are critical features as I just described. Basically, maintain activity, high capacity of multimodality, able to represent the rules and mapping, and not just a single stimulus. Okay, and importantly, it also has the ability to adapt and learn so that in future, certain tasks can be done faster. So current network can't do that. So we are actually trying to get new inspiration, how can we come out a architecture which is able to perhaps orchestrate different existing pre-trained network and do reasoning and do all kinds of domain adaptation. So if you look at, compared to memory, hippocampus, which is more episodic memory, and here it is more extracting the goals and the task rules. Okay, in conclusion, I think we would like to still use human intelligence as our role model. And then neither collection of task-specific skill nor general learning ability, like those IQ tests, are good benchmark. Because the first one it's not going to generalize, it can even imply shortcut. The second one could be too abstract and not grounded in real world. And humans are both specialized, born with prior experience, crystallized intelligence, and general capability. So how can we combine these two together? Okay, so our definition of AGI will be a collection of specialized skills, but with the ability to adapt, select the right skills, adapt them, integrate them for unseen situations. Okay. Right, so I think I will stop here.
Yeah, thanks to Hwee for giving a very comprehensive views on what is the AGI, history, benchmark evaluation, all different aspects, and also introduce some of the interesting kind of computation and techniques and so on. So now we have some time to ask the audience to ask some questions.
Okay, thank you for the very interesting talk. So basically, in the last talk you mentioned about the frontal cortex. So I'm wondering, like you also mentioned attention. So in the frontal context, one of the very important regions is called the frontal eye fields, which is directly connected to the gaze, which is like directly reflects the attention. And also the recent research also shows that like the working memory is highly relevant to the gaze. So I'm wondering, do you have any, so currently I'm doing this kind of research. I'm wondering, do you have any insight on your current research with the frontal eye fields and the gaze?
Currently, we do not have some work on that yet, but you are right. So our visual attention, like what Mengmi has presented, right, is precisely the how we select the right features in the environments. You know, I mean, why human being is so intelligent is that given a context, I mean, of course, there are different levels of intelligence. Some people can immediately spot what is really important in the environment. So beyond visual attention, so we are talking about non-visual attention as well, right? Given a problem which is represented somehow in the working memory, how can we pay attention to the right parts? And this working memory has to sustain the activities of the input and then find the right one, and then perhaps encode them into a representation and retrieve from the backend the different cortex and find the most similar past experience, and then how we adapt that to a new problem. Yeah. So I think these are the process that we would be interested to look at. Yeah. I also have someone looking into behavior learning as well. Yeah. So we realized that behavior learning for some of the still the OCR kind of problem, we actually have some results that show that they actually can outperform backprop in terms of the efficiency and the training set, and the noise is present as well. Yeah.
Okay, thank you.
Thanks. Any other questions from audience? Okay, maybe I ask a question. So the very interesting talk. So the AGI sounds interesting, especially this ChatGPT and GPT-4. Sounds somewhat quite successful. Do you think if the AGI becomes very, very successful, will this kill a lot of different, let's say, machine learning, NLP, and computer vision will be killed by AGI? Just want to get your view. Yeah.
I mean, definitely, if we can succeed in getting this AGI, I guess it's a combination of all these capability together lah. But of course, I think we still need specific skills. So as in my slide shows, the idea is that we should still have pre-trained models specialized in certain things, but we are able to reuse them for new tasks and contexts.
Okay, yeah, thanks, Hwee. So basically, the AGI is still built upon a lot of things people are doing, and also in the end, we can leverage AGI for many specialized downstream applications as well. Yeah, many thanks to Hwee. Yeah.
Thank you.
There's a question from online side.
Oh, really? Okay, the question is, backprop only assists in deep learning, whereas it's not proof that brain does the same. How we see backprop taken advantage to do well than humans? I think it's still arguable. I also have read some papers that there are people who still try to prove backprop is biologically feasible. Okay, there are two schools of thought. Some say cannot, some say it's still possible. But to me, depends on our need. If our goal is to understand the brain, then of course we can continue to do this to see whether backprop is biologically feasible. But if our goal is to build intelligent machines, we do not really worry about whether backprop is faithful to the brain structure. As long as we have different tools, some are inspired from the brain, some are not, some are purely mathematically driven. I think we can all put them together as a toolbox. Yeah.
Yeah. Thanks, Hwee.
Yeah. Thank you, Professor Li. Thank you for your introduction. So, good afternoon, dear colleagues. I'm Xiaoyu from the University of Tokyo and RIKEN AIP Center. In this talk, I will introduce our ECCV paper. learning mutual modulation for self-supervised cross-modal supervision. I'll first introduce the research background of cross-modal supervision, then introduce our work, experiments and discussions and conclusions. Okay, let's get into the first part. Well, images in LiFi existed in various modalities such as visible RGB, depth, digital elevation model, and thermal. These multimodal images play important roles in understanding the different physical properties of things and objects. For example, in this RGB remote sensing image, we can obtain the semantic information of objects. We can see these are plants, this is a road, and in its digital elevation model counterpart, we can obtain the height information of objects. However, there is a problem with the resolution of multimodal image data. Well, we can easily acquire high-resolution visible images which are of large size and full of spatial details, but due to sensor limitations, the non-visible images are usually in low resolution. As can be seen, they are of small size and lack of spatial details. And the low resolution property of non-visible images hinders their applications in practice and introduces the necessity of developing cross-modal superresolution techniques. Cross-modal superresolution aims to increase the resolution of a low-resolution source modality by using as guidance the structure cues from a high-resolution get modality to predict a super-resolved source image, of which the resolution is expected to be feasible to the high-resolution get, and the modality characteristics is expected to be feasible to the low-resolution source. And current cross-modal superresolution methods can be categorized into supervised methods and self-supervised methods. Among the supervised methods usually train super-resolution networks using a large amount of training data and require the supervision from ground truth. A limitation of supervised method is that these have a limited performance in real-world scenarios because large-scale training data with ground truth is hard to acquire. As we mentioned before, the non-visible images are usually low resolution. Different from supervised methods, self-supervised methods perform online learning on test data. That is, if we have a low-resolution source image and a high-resolution get image, yes, only a pair of images, we can then start to train self-supervised methods. Self-supervised methods do not require any external training data and do not require the supervision from ground truth. So they can easily overcome the difficulty of collecting training data, but also makes the task quite challenging. Specifically, one problem is that the low-resolution source image and high-resolution get image are from different modalities. So they cannot form a direct low-resolution, high-resolution mapping. In this case, it is very challenging to train super-resolution networks. Another problem is that we do not have ground truth, yet the supervision from high-resolution source is missing. This makes achieving results with both high-resolution and feasible modality characteristics another challenge. To overcome the first challenge, one of the previous self-supervised methods downsample the source and get images to lower resolution and use the original low-resolution source image as a pseudo-supervision to train its networks. Another previous self-supervised method formulates the task as a kind of modality transformation. It uses only the high-resolution get image as input and uses the low-resolution source image as a weak supervision to transform the modality of the high-resolution get image. While succeeding in training their networks, they cannot overcome the second challenge and deliver results that have blurry edges or show non-visible artifacts. So overall speaking, before the presence of our work, robust self-supervised cross-modal superresolution was an open problem. To address the issue, our work developed a mutual modulation super-resolution model. Specifically, we tackle self-supervised cross-modal super-resolution by introducing a mutual modulation strategy, which includes source-to-get modulation and get-to-source modulation, and using a cycle consistency constraint. One thing to mention is that following other methods, before inputting the source image into our network, we first use bilinear interpolation to upsample it to match the spatial size with the get image. Okay, let's go on. In our two modulations, we develop cross-domain adaptive filters as basic operators. In the source-to-get modulation, the filters update the pixels in the source feature by targeting the pixels in the get feature to induce the source feature to emulate the resolution of the get feature. In the get-to-source modulation, the filters update the pixels in the get feature by targeting pixels in the source feature to induce the get feature to mimic the modality characteristics of the get feature. And we train our network with a cycle consistency constraint, in which the start is the low-resolution source image along with the high-resolution get image, and the end is still the low-resolution source image. In the forward mapping, our network with the mutual modulation strategy optimizes both the source and get images to make a prediction with resolution comparable to the get and the modality faithful to the source. In the backward mapping, we incentivize the consistency between the downsample prediction and the original low-resolution source input by minimizing L1 norm to establish a closed loop for fully self-supervised learning. So different from previous self-supervised methods which utilize pseudo or weak supervision in low-resolution space, our model starts from the low-resolution source, seeks an optimal prediction in high-resolution space, and then constrains itself by getting back the start. In this way, both high-resolution and the feasible modality can be achieved, and the whole process is fully self-supervised. To validate the effectiveness of our methods, we first compare different methods for 4-fold and 8-fold super-resolution of depth data on 3 benchmark data sets. The average root mean square error is used as the evaluation metric. The best results are shown in red, and the second best results are shown in blue. As reported, quantitatively, our method can outperform the previous 2 self-supervised methods and even state-of-the-art supervised methods by a large margin. In this page, we provide the 8-fold super-resolution results from different methods. As shown, our method can achieve results with both high resolution and feasible modality characteristics, showing clear qualitative superiority. This page provides more qualitative results, and arrow maps are provided for better visual comparison. As we can see, compared with the previous 2 self-supervised methods and state-of-the-art supervised methods, our method can produce results with lower error and finer edge details. We further compare different self-supervised methods for their performance and the noisy guidance. As we can see, our method shows stronger robustness to get images with heavy noise. And this is thanks to our mutual modulation strategy, which filters and updates both the source and get images by considering their correlation at a pixel level. In addition to the experiments on benchmark depth data, we also validate our method on real-world remote sensing data that cover digital elevation modality and thermal modality. For super-resolution real-world digital elevation model, our method achieves the best performance for both the 2 scale settings, and qualitatively, our method can better preserve the spatial details and modality characteristics of digital elevation model, achieving prediction closer to ground truth. And here we compare our method with previous self-supervised methods for the super-resolution of real-world thermal data. Although in this task, we do not have ground truths to perform numerical evaluation, but by comparing the results, we can see the superior generalization capability and super-resolution capability of our method. Well, a frequently asked question on our work is that why can it hard to perform even supervised methods? Indeed, supervised methods have shown promising performance in cross-modal super-resolution. However, they have two problems. First, they suffer limited performance because large-scale training data with ground truth is hard to acquire. Second, as we know, supervised methods cannot easily generalize well to test data that is not in the same domain with the training data. And the reasons of our superior performance are twofold. First, our mutual modulation strategy and cycle-consistent self-supervised learning effectively facilitate our model to achieve results with both high resolution and faithful modality. Second, the employed online learning scheme enables our model a strong generalization capability to any given input. So with robust performance and strong generalization capability, our method can outperform supervised methods. Next, let's move to the conclusion part. In this talk, I introduce our paper, Learning Mutual Modulation for Self-Supervised Cross-Modal Super-Resolution. It addresses an open problem in the field of cross-modal super-resolution and presents a robust self-supervised mutual modulation super-resolution model. And our mutual modulation strategy is demonstrated to be effective to tackle image data that have modality difference and resolution gap. Experiments on various tasks demonstrate the state-of-the-art performance of our mutual modulation super-resolution model. That's all of my talk. Thanks for listening.
Thank you. Thank you, Xiaoyu, for a very interesting talk, and also the result demonstrate the self-supervised learning beat the supervised learning-based approach. She also gave some of the potential reasons why this should be the case. Okay. All right. Now let's invite some of questions. Yeah.
Thanks.
Hello? All right, I can increase my own volume. Thanks, Xiaoli, for a great talk. I noticed some multimodality can have a natural corruption to some noise. May I know why? Is that true? Multimodality can have some natural corruption to common noise. If so, why? May I know your opinion on this part?
Are you asking about why our model can perform well in under noisy get images?
Yes. Yeah.
Yes, it is because in our model we have a mutual modulation strategy, and the mechanism of our mutual modulation strategy is update the pixels in one modality by targeting the pixels in another modality and considering the pixel correlation. So if in the task of super resolution and noisy guidance, the noisy are not the noisy in the get image is of low correlation with the pixels in the source image. So in our mutual modulation, we give low weight value to the noisy pixels, and so our model is has robustness to the noise pixels.
Okay, thank you so much.
Thank you, Jifeng, for good question. Any other questions from our audience? No. Okay. If not, I think we can close this first part of our presentation. Let's thank our speaker again. Yeah, thank you. The next session will be started at 3:35 p.m. Thank you, Mengmi, for your introduction. Yeah. Good afternoon, everyone. It's my great pleasure to visit RIKEN and hope can introduce some of our work in relatively broad level. We do hope to explore collaboration. I'm a researcher in A-STAR. I'm a part of CFAR and a part of another research institute. It's called Infocom Research. Just now, Hwee and Sheng are from this institute as well. I'm also holding adjunct position at the Nanyang Technological University. We do get some of PhD students by collaborate with local university in Singapore, like NUS and NTU, to supervise some of students under the A-STAR PhD scholarship. All right, and so today my talk is mainly focused on sustainable AI, some of the challenges and innovations, but a lot of this topic we also talk about in the other context. Okay. So I just give a little bit of introduction about myself. You can see I'm just my Google Scholar page. In the past, I'm doing one thing, it's called positive unlabeled learning. Actually, I gave this name in my paper 20 years ago. Basically, we usually doing a positive and negative training, but at that time, sometimes when we think about from practical perspective, we may not have the training data. Sometimes for negative data, how do we learn from positive and unlabeled data? So I just gave this name. It turns out I do publish a number of papers with my collaborator. It turns out that some of our top cited paper is from this positive unlabeled learning, a couple of papers in this area. Recently, I also focus on this time series sensor data analytics. This is because it has many different applications in healthcare, in semiconductor, in aerospace, and so on. I think this is interesting data to explore. You have the temporal dependency among the data and so on. And it has many real-world applications, right? Anomaly detection, diagnostic, prognostic, remaining useful life. It has really diverse real-world application. So this is today's talk. First, I will just give a high-level introduction about this background and what are the challenges, then give a few representative research or group has been doing in the past few years, including some of research like model compression, domain adaptation, unsupervised representation learning, edge and cloud collaboration, and so on and so forth. Some of this topic definitely has an overlap with RIKEN's research. Just now, I think Xiaoyu talked about the self-supervised learning, and Chen will talk about the constructive learning and so on. So I do see potential we can collaborate. So I think this sustainable angle becomes very, very important. AI has many applications, but AI at the same time consume a lot of energy, generate a lot of carbon and so on. So one of the figures is you train a transform model, you consume the energy which is equivalent for 5 cars, which is running over the entire life. So AI does generate a lot of energy consumption. So we believe it's so critical to take the environmental and impact into consideration in AI development and also deployment stage. So currently this large language model, we really need those supercomputer, a lot of these GPUs to build such kind of model. It seems only those big tech companies like Microsoft, Google, and so on, they can train them, okay? So how do we really do something, make this sustainable so that university professors, PhD students can also work on this? Also, we have this concern, so I asked ChatGPT, okay, how much energy does it take to train you, okay? So the ChatGPT does not directly give the answer as expected, okay? Keep it a secret, just say the exact amount of energy used during my training is difficult to estimate, okay? But it's safe to say training large-scale AI model like me requires significant amount of energy, both in terms of electricity consumption and the computing resources, right? So it's just say it could be several hundred to several thousand kilowatt hours of energy and so on, right? So it also mentioned that actually we should develop a lot of this energy efficient AI training techniques and hardware, which can be used to reduce the environmental impact of large-scale machine learning. We believe this is a very promising direction, and we should pursue such kind of research. So in STAR-CFAR, we do have some of the research direction. One is how do we make. Secondly, is leverage AI to address some of the sustainable issues, let's say climate change or the others. Hopefully, we can do a lot of such kind of work. Recently, Prof. Ng and our team in STAR-CFAR, actually, we just did a survey paper on this sustainable AI, which is accepted by this IEEE Computational Intelligence magazine. So we summarize a lot of research in this area, which can be categorized into the 4 categories. So one is a computational efficient AI, right? So one of the aspects is to try to compress a model. AI training consumes a lot of energy, but at the same time, the AI model are deployed for real-world application. According to some of the estimation, it consumes even more energy than training a model, okay? That's why sometimes we can compress a model, make a model concise yet accurate, will be very useful for model deployment. The second aspect is data efficient AI, right? A lot of work here using the less labeled data through active learning, few-shot learning, no labeled data, transfer learning, self-supervised learning, those contrastive learning sort of approach will be pretty much very promising research direction, right? So in addition to computational efficient AI and data efficient AI, other aspects will be responsible AI and rationalizable and resilient AI. So we believe these are all relevant to sustainable AI. Okay, all right, so yeah, so as I mentioned, we are actually focused one of the area is time series sensor data modeling and analytics. I think it's because of very, very important research area and topic. We can do diagnostic, prognostic, and so on and so forth. So in the past, we are doing some of the conventional machine learning. Later on, we are using a deep learning, proposed deep learning approach to learn a good representation, as well as a transfer learning and the model compression approach and so on. So our group actually published a lot of paper in this area, and we win some of the best paper award, and some of our paper has been cited by more than 1,000 times and so on. I think this is some of the area our team actually focus on. And also, this can be also, we are going to do the sustainable time series data analytics. So I would like to share a couple of research. This, one of the research we have done is this model compression. Basically, no matter a large language foundation model and so on, or some of other model, how do we compress a big model into a smaller model while keep its accuracy will be critical, right? So we have this research, and what is the key idea of this research? Basically, we develop some of measure to do the knowledge distillation. How do we pass the knowledge from a teacher to student, right? We can build a teacher network. Let's see LSTM. From time series sensor data, we extract some of the good feature representation. Then we build some of the model, let's say regression model, classification model, to do the prediction. At the same time, we want to build a smaller student model, let's say could be CNN, okay? So it also can extract the feature. All right, so we just want to have a two-step. One is a feature distillation, one is knowledge distillation. For feature distillation, we just want to make sure the feature extracted from teacher and the feature extracted from student align well, okay? So go through this adversary-based training, right? So your discriminator try to identify whether this feature extracted from teacher network or student network, right? And the student make use of this generator CN to extract some of the feature. We try to align. At the same time, for knowledge distillation, we try to align the predicted label. As well as if we have a ground truth label, we will try to align this data with a ground truth prediction, just like a supervised learning, right? So we basically integrate all these three laws together. We can build some of the good model to pass knowledge from teacher to student. So this is some of the experimental results. We are using 4 data sets and 2 evaluation matrix, okay? We can see this is the result of a student network. Then this is a result of teacher network. It seems the teacher network perform much better than student network because this is more like error rate, smaller, better, right? So at the same time, we use our knowledge distillation-based approach. We can see we achieved a very good result, which is pretty similar to the teacher. In a sense, we compress model, but still keep the accuracy. So we also compare the size of the teacher network and student network, as we can see from the bottom side of this figure. In terms of number of weight and the total floating point operation, the network is much smaller. Okay, so this is pretty much interesting work. This just give you one example from our research. How do we compress a model so that the model can be used in the edge site for some of the real-world application. So the second work is more like a time domain adaptation. So this is quite pretty much some of the topic a lot of people are talking about. So one of our research is also trying to, from source domain, you can build some of a model, you have sufficient label data. Now how do we make use of this model in the target domain, right? So here we also try to align the feature extracted from the source domain and the target domain. And then in the end, we just make use of source domain model to do the prediction. Actually, this also has some sort of a privacy preserving aspect. So in addition to this, we also try to keep some of the characteristic of the target domain. For example, we try to maximize the similarity between the target data and the target feature by using this info NEC loss, okay? So we basically integrate from machine learning angle, we have this discriminator try to maximize the similarity in terms of feature. We have this info NEC loss try to maximize the mutual information between the target signal and the target feature, right? So this is our research for this. And recently, we also want to expand this unsupervised domain adaptation to multivariate time series data. So we can see source domain and target domain, you have a multiple variate, let's say different sensor, right? So let's say vibration, temperature, and so on and so forth. But in this case, we try to partition all the data into different segments. Each segment, we can build some sort of a graph representation, let's say using graph neural network sort of things. Then we try to do the multiple alignment between the source and the target domain, which includes some sort of a spatial temporal kind of alignment. Because if you are from same sensor, you should somewhat align, okay? If you are, how do you model the temporal dependency? Previous signal will affect later on the follow-up signal and so on. Okay, so yeah, next, I talk about the unsupervised representation, which is also currently a lot of work used for image data, right? So we also think about it, those methods proposed for image data may not be used very well for time series data, which didn't address the temporal dependency in the data, right? So in image data, sometimes people want to create multiple view by using some augmentation techniques. For example, the color distortion, rotation, but you cannot use it for time series data, right? So in this case, we basically propose some of the techniques based on this contrastive learning approach, which is try to maximize the similarity among a different view of the same example. This is just like Chen mentioned, this is some sort of a positive pair, and then we minimize the similarity with other sample, which is a negative pair. So this is a pretty straightforward idea of this, but we also propose two types of contrastive learning or time series representation learning. One is temporal dependency, temporal contrasting, learning the temporal feature with a tough cross-view prediction task, okay? And contextual contrasting, which further learns a discriminative feature, right? So we just want to give a high-level view. We have the three laws here. In machine learning, basically, we try to do the two things. One is a temporal contrasting, okay? We try to using the multiple argumentation from a signal. You create a strong argumentation, you create a weak argumentation. Then you try to do the cross-view prediction. As in using the representation from time 0 to time t to predict time t plus k in a cross-view manner, okay? Using the representation from strong argumentation to predict the future of a weak argumentation. Then you also use the representation from weak argumentation to predict the representation of the strong argumentation for the future, okay? So this is two laws. We use a contrastive learning, remember, maximize the similarity from same example and minimize the similarity from different example, right? At the same time, we also have this contextual contrasting, which is basically maximize the similarity from same segment of this time series data, right? Yeah, I think we are doing many experiments, but here I just want to highlight in this semi-supervised training setting, where we compare with supervised learning-based approach. So supervised learning, you are doing an encoder and classification and so on. Basically, all use a supervised learning, but for us, we use self-supervised learning to do it encoder to do some representation learning. Then we do the classification. So we can see when we have a limited training data, let's say 1%, then our proposed approach, which is able to achieve much better results. But when training data becomes more and more, these two approaches pretty much generate a similar sort of result, even though sometimes self-supervised learning may be able to generate better results, okay? All right, so yeah, so we are talking a lot on this sustainable AI. So one recent approach of work we have done is in the edge side, sometimes the edge device, you want to use some of the smaller model because you don't want to basically make the battery consume a lot of energy and no energy in the end for mobile phone, for example. And in this case, how do we coordinate from edge device and cloud to make it more sustainable of the AI model, especially during the deployment stage becomes pretty important, okay? So we collaborated with some of the UK university to do this research. So basically, we have some of the probability accuracy estimator. Just in the edge side, what is predicted accuracy, okay? In the cloud side, usually will be much more accurate. In edge side, if we feel not so confident to make a great work for prediction, then we send the data to cloud side, and the cloud side make a prediction to notify the user, then you can try to update your model and so on, right? But if the local computing resources is sufficient enough to do a good prediction, we just do it in local, right? So this is try to, and the first time, try to understand this energy consumption, save the energy, at the same time, we want to guarantee the accuracy, right? So take both of these into consideration. I think probably it's time to finish, but anyway, so next, in addition to, we are working on some of this fundamental AI research, but we do want to leverage some of the capability we built from fundamental research for real-world application. I think Hwee's team more focused on how do we leverage computer vision to detect some of the aircraft defect and so on. Our team worked with Singapore Airline more from a time series sensor data aspect because airplane has more than 1,000 sensors, okay? we try to do this aircraft component anomaly detection by making use of unsupervised learning, supervised learning, and semi-supervised learning, and so on to detect this. I think this research has been highlighted in the Discovery channel. And also the model has been deployed in Singapore Airline aircraft infrastructure. So we hope we can generate some more real-world impact.
We try to use the latest technology to shift reactive maintenance when something pops up at an untimely occasion to predictive maintenance so that we can do something proactive before it actually fails.
SIA Engineering Division is able to access thousands of sensors worth of data, some recording it up to 8 times a second, to detect precursors to potential problems weeks in advance, such as, for example, an engine part which may be running just slightly hotter than normal, or airflow that appears to be marginally slower due to an obstruction building up. By working with agencies such as the Agency for Science, Technology and Research, (STAR), and using artificial intelligence methods such as machine learning to examine sensor data, this system can flag problems before anything can go wrong.
All right, so this basically give an example. Some of the fundamental research can help us to do some of the industry AI to generate some real-world impact. This is some of A-STAR's mission. Finally, I just want to conclude my talk. So the AI model has been widely used in our daily life, but in the training, its deployment consumes a lot of energy, right? So we really need to make the AI model more sustainable and generate less problem for the impact of our environment and so on. So yeah, many different aspects of how to make this AI model sustainable. So here we just talk about some of the representative research from our group in terms of model compression, domain adaptation, unsupervised representation, edge cloud collaboration, and so on and so forth. So this bottom part is one of the slides that I attend this supercomputer Asia. One of the presenter, he talked about this, maybe it's not so visible, but what he estimated is this during the inference stage, actually the cost is far exceed the training cost when during deploying a model and any reasonable skill, okay? So it requires 3,800 server to run the inference, which is very, very time consuming. Estimated cost is $700K per day, okay? So this is a problem for during the deployment stage. So some of the research might be important to address this problem. Of course, there are many interesting research we can do it together, possibly by collaborating with RIKEN AIP. For example, how do we do the core design of the AI model? How do we do the energy-aware design? How to do the model sharing? Not necessarily everyone try to build some of the very big AI model. How do we share? How do we refine, fine-tune so that we can still get an accurate AI model but use less energy? Okay. How do we unfold the complexity of the AI model are all the important problems we can explore. Yeah, with this, I want to conclude my talk and looking forward to have any collaboration opportunity with researchers in RIKEN. Thank you.
So we still have time. Let's take 1 to 2 questions, please.
Regarding the collaboration of cloud and edge devices for collaborative learning, so you need to evaluate the result is good or not. Then you decide to query from cloud or not. So why do you evaluate it in local device, and how do you evaluate the result?
Okay, very, very good question. So basically, your question is why the number one is why do we evaluate in the local instead of in the cloud? I think because we assume the model has been deployed locally, right, in your device. This model also is not so complicated deep learning model. Otherwise, your mobile phone, we want to do, let's say, activity recognition. If you deploy some of the large-scale AI model in our mobile phone, probably the energy consumption will be pretty large, right? But in cloud, we can use this large deep learning model to do the prediction. So we want to deploy this model in the edge device, but it is a smaller model. Usually smaller model may not be that accurate compared with a big model. So mobile phone can do prediction. Some of this, let's say 800 can also do the prediction, but 800 make use of a large model. So in this case, a smaller model used in this device, they consume much less energy, but unfortunately, it may not be so accurate, right? So in this case, we do need to have some sort of estimation of the error. So we do have some of a probabilistic based approach to basically estimate the potential error. Basically, whether this, when you have a new example, you want to see this activity recognition, what kind of activity you are doing. So in some of cases, we do estimate what is the probability they belong to the different class. If the probability is basically not so sure, maybe 10%, 10%, 10%, let's say you calculate some sort of entropy, sort of estimation, what is the overall confidence sort of value. So if this value, we still have some threshold, unfortunately, but when this threshold is larger than certain things, then we are basically, let's say 50-50, your entropy is largest, right? If you're a binary class. If 90 and 10, the entropy will be small. So we will basically have some sort of estimation, error estimation, to make a decision whether we should send this to the cloud or not, right? When we are not so sure, then we send to cloud, so that the cloud makes some of prediction that maybe also update the model using limited training data. But at the same time, if we are very confident, we just use it in the local. This is basically high level idea. Yeah, thank you. Very good question from GP. Yeah, thank you.
Any more questions?
Thank you very much for this talk. I have a question about how we can do edge learning. So the one that you mentioned, where we have a part that is first machine learning model run on devices, and then we have a part that is run on clouds. Knowing that now more and more companies are not disclosing their models and only providing APIs, I feel that the on-device part is disappearing, so there will be only the API parts. So I was wondering what's your opinion on this trend and how your protocol can support this new way of learning.
Okay, I'm not sure if I understand your question very well, but personally, I feel usually if we can do it in the local or device, usually it will be good. It will save some of the energy. But if you use a certain big model and API, but you don't want to frequently query them, right? If you frequently query them, you also consume some of the energy in our side. Maybe you have additional cost, right? So usually we need to strike a balance. We have a distributed machine learning. One is in the edge side, one or something through API for a cloud. How do you strike a balance, right, between the accuracy and some of the cost, other costs into consideration? So personally, I think this need to have some deep thinking to see how do we better do it. Yeah, I also need some time to think. Yeah, okay, but it is a pretty interesting question. Yeah.
All right. Okay. All right. So let's thank Dr. Li again for his amazing talks on system-level AI.
Yeah. Thank you.
My topic today is the efficient sharpness-aware learning. Before that, I want to quickly go through my background. So I started my journey. I started my research journey at the NTU. I completed a PhD there. And after that, I also joined the Sony US Research Center at that time. But when I stay in NTU, actually my research focused on the robustness, especially the transfer learning and the virtual training. So yeah, we have published some papers on that topic. During I stay in Sony Research, I realized very important to study the efficiency of the machine learning. So that's something gained from the industry experience. So for the efficiency, this topic we also publish some papers. We're particularly interested in model compression and the efficient training. And after that, I joined STAR and also have a adjunctive faculty position at the NUS. So except for the robustness and efficiency in AI, I'm also interested in applying these techniques and develop algorithms in real-world applications, especially on-device AI applications. So when I stay in Sony, I'm part of the Sony autonomous driving team. Okay, so I'm one of the senior research engineer who developed the Sony Vision as the autonomous driving system, especially for the vision part. So I'm also interested in some other applications like eye blink detection. Why is it useful? Because it can help us, especially in autonomous driving car, help us to detect the fatigueness of the drivers. So it's very important. So all this works actually. Our team has several best paper awards and also some we won some challenging prize in international competition. Oh, okay. So I'm interested in robustness and efficiency, and today the topic is actually in the intersection between the robustness and efficiency. Okay. So this is my personal background. This is the introduction of my group. My group I call it ZHOU group. Okay. Z stands for the zero carbon, H stands for high reliability, and O stands for open environment. For example, the domain adaptation, noise label, I believe is a lot of the issue, research problems in open environment. Unbiased AI, we believe we should develop a trustworthy machine learning framework. So that's why I explained the ZHOU for my group name. The second below, okay, the second below are the scientists and the research engineers in my group. Basically, we have the 5 research scientists and 3 research engineers, and 3 research engineers here are actually doing part-time PhD either in NUS or NTU. Okay, I also have the several PhD students. Okay, some of the co-supervisor students, some of I'm the main supervisor on our A-STAR scholarships. Okay, so our group also hosts a lot of visiting scholars, visiting professors, as well as the visiting students. So I want to do a small advertisement here. So I do have the 1 head count in my group. So if you are very interested, you can feel free drop us an email. We do have the scientist position immediately available now. Yeah, you also if you find our group research work interesting, you also can drop an email to seek any potential collaborations or visiting positions. Okay, let's wrap up the first part. Begin our journey of the main topic here. As we know, training a large scale deep learning model is quite hard. Okay, so that's something will usually happen. The sharp local minima. So what's the consequence? What's the negative impact of the sharp local minima? So the black curve is the testing function. If we have the sharp minima here, which means if we have the testing function, the red curve shows the testing function. So normally the training and the testing function has a small shift. It's a reality we cannot avoid. So even small perturbation on the minimum we generate from the deep neural network can lead very huge gap for the we call it the generalization gap. That's the undesirable consequence for the sharp local minimum. I give you another example. We call it the flat minimum. So this is the flat minimum. So if we do have the small perturbation on the minimum we have for the deep learning system, okay, we can see the gap is small compared to the sharp minimum. So in reality, we actually prefer the flat minima rather than the sharp minima. The question is how to do that? Thanks for the sharpness-aware minimization. In short, we call SAM. SAM is a technique helping us to find the flat minima, generates better. Okay, so this is the first figure shows is the original loss function landscape. Okay, the second figure shows that after the applying the SAM, we have the flat minima. So, but we're looking at the accuracy, testing accuracy. We find that original SGD, right, optimization techniques. We have the this 80 something, 82 something the test accuracy. When we apply the SAM, actually we can boost up the performance. Okay. So SAM is very good, can help us to generate the better performance in terms of the accuracy, testing the accuracy. But when we're looking at the training speed, yeah, that's the issue of the SAM. We can find that the training the SAM is much slower compared to the normal SGD training. So almost doubles the training cost. That's the issue we want to solve. So can we have the perfect solution that we want to enjoy the both efficiency and the performance at the same time? Okay, so that motivates us to promote to propose the efficient SAM. Okay, so before I introduce my our proposed method in details, I would have a look why the SAM doubles training cost. Okay, to seek a flat minimum, SAM regularizes the sharpness by this gap. Okay, so basic idea is that if we add some perturbation on the parameter space, before and after, that's the gap. That's how we measure the gap. So basically, we want to find the maximum gap within the perturbation, this neighborhood. Okay, that's how we measure the sharpness. So how to solve this optimal epsilon? Find the best, find the solution for the epsilon here. So basically, we want to apply the first order Taylor expansion. So based on this technique, we can find the solution for epsilon hat. Is that it's a gradient of the original loss function. Okay, so which means that we have to compute the gradient to find the optimal epsilon. But that's not the end. We also need to compute the original loss function. So that's why we have the 200% of the training cost for the same. That's the issue. That's the breakdown of the issue. Okay. So next, so the first part, this is the sharpness measurement. So we need to have to compute the gradient. This is the original loss function. So we have the 200% training cost. So yeah, we have to compute the optimal solution for the best perturbation here. After that, we substitute back into the original loss function to compute the overall objective. That's to expand 200% of the training cost. So our proposed method, how to reduce the computation overheads. So there are two dimensions of the parameters of the factors we can play the optimization. The first one is that we can reduce the computation over the theta. That's the parameter space. Also, we can reduce the computation over the training set. That's S, the subset of the training samples. So our idea is that we want to reduce the computation overheads of both weights and the data. Okay, let's introduce the first one. So how to reduce the computation over the weights. So basic idea is that we propose the stochastic weight perturbation. The overall idea behind that is we want to provide backpropagation through a few weights. So very simple. Every backpropagation will just randomly select some weights. Every time, different weights. Okay, so the next question is why fewer weights can still improve the performance? Okay, so we also give the explanation, right? Just recall the same epsilon solution. So basically, it's based on the linear approximation. So assumption here is if the L function, original loss function L, is linear, then we can have the perfect solution here for the epsilon, right? So, but reality is that L normally is not linear, right? So, but that's why we call it more linear of the loss function, better approximation we can have. But reality, the L is not so linear. So if we apply the sparsity on the width, we find that, experiments find that the sparsity is parameterized by the beta here. So larger beta, a smaller beta, more sparse of the loss function we generate. So that's why we have the better performance. Okay. So sparsity promotes the linearity. Linearity has the better approximation. That explains why our proposed method works better. Okay, another dimension is how to reduce the computation on the data selection, on the data set. So basic idea is we want to select fewer data, okay? So, but actually we cannot randomly select the data. So in this case, we want to select the sharpness sensitive data. So how to do that? We break down the batch into two subsets. One subset is called positive B. The second subset is called negative B. So the positive B is that the loss function is positive. Normally we set the alpha here is threshold. We normally set here is the 0. Okay, it's positive direction, and that's denoted by this blue arrow. The second direction called negative directions. So in the paper, but of course here we know the minimization sharpness of the two directions are different. So in the paper, actually we show that the data selection is a strategy if we only minimize sharpness over the positive subset. Positive B can help us to still achieve the same results, because we can prove that the optimization over the positive B, and this subset is upper bound to conduct the optimization of the whole batch. Okay, that's the idea. Okay, so let's look at some experiment results. And we compare with the SGD and the SAM. Okay, we found that the efficient SAM actually can achieve a better accuracy, testing accuracy. We also improve the training speed by large margin. Okay. Now this is a ablation study for the two techniques which we proposed in the previous slides. One is for introduce the sparse width, another one is the data selection. We find that the two techniques are effective. Okay, can improve the accuracy as well as the training speed. So training speed here we use the within 1 second how many images we can process. Okay, so this is the visualization results. The XY is the parameter space we projected to two dimension. Z is the training loss. We have found that the SAM compared to SGD has a flatter minimum, but our efficient SAM can actually promote even more flatter minimum. That's the explain why our efficient SAM works better than the SAM as well as the SGD. Okay, that's the work for our first work. Published in ACLEA 2022, we released our course to the public, so feel free to download to play with it. Okay, so let me introduce our second work on this direction. So one question here I pose here is that could the SAM could be more efficient? So this figure shows that this is a SAM or vanilla SAM. This is the efficient SAM, or just in previous slides they introduced that, right? We'll compare to the vanilla SGD. Even though we have the higher accuracy, the y-axis shows higher accuracy, but we're talking about x-axis training speed. still far behind the vanilla SGD. So next question is that, can we come up with a better solution to further reduce the additional cost to efficient SAM to almost zero? That's our answer, SAF. In the second one, we propose a method called SFAF, SAM sharpness minimization for free. Okay, that's in short we call SAF. So our method actually has almost the same training speed as the vanilla SGD, but at the same time we have the better accuracy. Okay, so how to do that? Let's recall where the additional computation is coming from. So sharpness measure and vanilla loss, we have to compute the gradients for twice, right? The previous work efficient SAM, we try our best to reduce the computation we cost on the parameter space as well as the data selection part, but we cannot avoid compute the gradients. We just reduce the computation of the gradient. Okay, so in this work, sharpness-aware training for free, we intend to approximate the sharpness measurement without the additional computations. We just totally forgot we should totally avoid the computation of the gradients. Okay, what is the sharpness measure? So these two figures shows that the sharpness in the same measures the largest change of the loss within the neighborhood. So we possibly to use this intuition to replace the original measurement of the sharpness. That's all. So these two figures of the flatter and the sharp minima shows that the loss drop speed actually is another measurement to measure the sharpness. So in this case, we want to use trajectory loss. So basic idea is that we want to use the KL divergence between the different imports on the same batch. So in this case, we avoid computation of the gradients. Okay, but we still can reduce the sharpness. So that's why our SAF can avoid the sudden loss drop during the training, still promote robustness. Of course, we are bringing a lot of memory issue because the KL divergence here, right here, we need to store the index outputs of the order training samples. If we're facing the image net, let's say 1 minute or 10 minutes of the training samples, actually is a very huge overhead, huge cost in the memory. So how to do that? We further want to reduce the memory cost. We propose the exponential moving average to construct the trajectory loss. So more details, you probably can read my paper offline. So we compare the SAF, the efficient one, memory efficient one, we call the MESA, and we list down, we have the consume only less than 100 megabytes for the ImageNet data set, much smaller compared to the SAF, the previous proposed method. This is the results. We show our superiority in terms of the efficiency and the testing accuracy. Okay, so I think this is a visualization. From the first row, we showed all these are same variance, our proposed method, and the vanilla set shows can generate the flat minima, right? But the second row is the zoom out figures shows that we have still shift the batch better in terms of the seeking the flatter minima. Okay, this is our second paper public the codes. Okay, feel free to download.
Thanks, Joey, for his great talk. We have some time for 1 or 2 questions. Yeah, I have one question.
Yes.
I know that SAM or efficient SAM, even your new SF SAM, also have to decide the size of epsilon.
Yeah, size of the epsilon.
Yeah, do you have some principal way to decide the size of the epsilon?
You mean
how large you can?
Yeah, you mean this part, right? Normally, we just empirically said that this rho here should be a very small number value, just like the adversarial training. There's there are no particular guidelines of that.
Okay.
Okay.
Thank you.
Thanks.
All right, that's again for our speaker.
Thanks.
Hi, I'm Kazusato, first year master student in the University of Tokyo, supervised by Professor Tai Suzuki, and also intern in the deep learning theory chain of this RIKEN AIP. My interest lies in machine learning theory, especially the intersection of generalization and optimization of neural networks. Today's main topic is the analysis of the diffusion model as a distribution estimator using the statistical learning theory. This is a joint work with Shunta and my supervisor, Tai Suzuki. Okay, so first of all, look at this picture. Also, I think most of you machine learning guys know this picture, but suppose that this was the first time for you to see that picture. Then you would feel how beautiful it is. You definitely think that this is painted by some skilled human, but not in reality. The fact is that this painting is an output of Mid-Journey, a machine learning model. Specifically, Mid-Journey is a diffusion model. Oh, I think the battery is now. Okay, thank you. In the last 3 years, we have witnessed the groundbreaking success of diffusion models in image, video, and audio generation. Also, I'm showing here several pictures I made with stable diffusion. They represent necessary characteristics given by the text input quite well. So, well, I think that's enough to explain the motivation for developing theory for diffusion modeling. But before introducing what kind of theory exists and what kind of theory we develop, we need several preparation mathematically. Yeah, so let's begin with an intuitive explanation of diffusion models. Let's consider the so-called fold process. So starting from one of the training sample, and at each step, we add noise to the image from the previous step gradually. And through this fold process, the data vector is converted to the random vector following the Gaussian distribution. Then, according to the most prevalent explanation, by considering the reversal of the fold process, we can generate the data following the true data distribution from noise. But I'd like to clarify the meaning of the reverse, time reversal a bit more, because it's necessary. For this, we introduced the formulation by Tsang et al., the formulation of the fold process as a stochastic differential equation. So taking the interval of steps into infinitely small induces a continuous time dynamics described by the corresponding SDE, but it's quite simple. So let xt be the vector at time t, then xt follows this equation with the d-dimensional Brownian motion bt. So this means that infinitely small change of xt plus dt from xt is determined by xt and this added noise term. So similarly to the discrete time case. And for later use, this distribution of xt at time t is denoted by pt. And from definition, P0 is a distribution of the true data. So please remember this. And I also note that because we are simply adding the Gaussian noise, the distribution of xt conditional, or in other words, starting from x0, follows the Gaussian distribution with mt and sigma t defined as this. So it's quite simple, Based on this, the distribution of xt pt can be written as a convolution between the density function of the initial data distribution and the Gaussian type kernel. Yeah. Now, the backward process is formulated. Just as the most ordinary differential equation has their time reversals, we can consider the time reversal of the stochastic differential equation under some conditions. So let us stop the fold process at some time over line t, then consider the following stochastic process y. So sample y0 from the distribution of x at time over line t, and make yt follow this stochastic differential equation. Then the distribution of yt matches to that of x over line t minus t. So in this distribution sense, we are saying time reversal. Thus, if we can simulate this stochastic differential equation with a perfect accuracy, then we can obtain a data that follows the target distribution. So this is the basic mechanism of the diffusion modeling. However, there is a critical problem, that is, the exact value of score cannot be obtained because the distribution of xt at each time t essentially depends on the true distribution p0, but we have an access to p0 only through a finite number of samples. Therefore, we necessarily replace the score by its approximation with a neural network called a score network. Also, p over line t should be replaced by the Gaussian distribution, but we do not get too much into this here. So anyway, in every real diffusion model, score should be approximated by a score network, which is trained by n sample. But how? The following theorem gives one insight. This found the KL divergence between the data distribution and the generated distribution by an integral of the L2 loss over OT. So this is called a score matching loss. However, the right-hand side still is an unknown quantity, so we cannot find a score network that is a minimizer of this score matching loss. So again, how should we train the score network? So because the score matching loss is a kind of population loss, we consider its empirical version. This score matching loss is equivalent to this quantity up to a constant independent of score network. So here the important point is that expectation with respect to x0, the true data distribution, and xt given x0, the conditional distribution of xt. And moreover, here the functions that only depends on xt given x0. So expectation with respect to xt given x0 can be computed at an arbitrary accuracy by making many paths from x0. So because that follows the Gaussian. So therefore, we only replace the expectation about x0 by n sample data following p0. And this empirical score matching loss can be minimized once the n data is obtained, if we have sufficient computational resources. Yeah. By the way, we also remarked that here the lower limit of the interval is truncated by underlying t. This is because the score blows up in general as the t approaches 0. So no neural network can make this error other than infinity. So we make truncation. Okay. So, and we also remarked that practically the expectation with respect to xt given x0 is also replaced by a finite sample, and integral over t is replaced by a sample of t. Then the expectation score, empirical score matching loss is finally reduced to just the square loss minimization problem. So yeah, actually taking a finite sample of t and xt is suffice to obtain the suffice to obtain the same quality of solution that is minimizer of this empirical score matching loss. Yeah. So finally, we would like to introduce what our analysis is. So as we have seen, diffusion models implicitly run the true distribution in a sense that it solves the empirical score matching loss and use the training neural network to generate the data. Thus, the natural question is, how good is the diffusion modeling as a distribution estimator based on finite n data? That is the problem we address from now. But regarding this question as a distribution estimation problem using the framework of statistical learning theory, we assume that the true data distribution belongs to well-known function classes, and a score network is selected as a minimizer of the empirical score loss over a certain class of neural networks. Then we evaluate the distance between the generated distribution with the selected neural network and a true data distribution in total variation distance and Wasserstein distance of order 1. Yeah. So I briefly explain the existing ones. Most of the existing analysis focus on the propagation of the score estimation error to the final estimation bounds and the discretization error of the SE, assuming that the bounded score estimation error has given. So among them, recently Chen et al. Shows a bound in the total variation distance that polynomially depends on all parameters. If the L2 loss between the score and the score network is bounded and the score is smooth uniformly over OT. However, our question is how much we can minimize the score estimation error is unknown in the first place. So the only exception, the generalization error analysis was given by Ivor et al., but their analysis is n to the power of -1 over d. However, due to the limitation of their truth, it is impossible to extend the result to a formal density estimation problem where the faster convergence rates are expected depends on the smoothness of the true density. Yeah, so we introduced our additional problem setting in 2 more slides. So we assume that the true distribution has bounded support and the upper and lower bounded intervals, and most importantly, belongs to a Bezout space, BPQS. Now, among the 3 parameters of the Bezout space, S is the most important one because it represents smoothness. The Bezout space includes many well-known function space. For example, the Held space, a space of, roughly speaking, S times differential function with its derivatives but bounded, is included in the Bezout space, BS infinity, infinity. So also, as a technical assumption, the data distribution P0 is assumed to be sufficiently small on the edge of the support. And we define the hypothesis class of neural networks for the empirical score matching loss minimization as a class of sparsity constraint layered networks. This is characterized by 4 parameters, L, W, S, B. So L, W, B bounds the depth, width, and the value of the parameters. So it's quite usual. And S corresponds to the sparsity constraint, or the number of non-zero parameters of the network. The motivation of introducing these parameters is that sparser networks have smaller generalization error. So such a class is frequently used in estimation theory using neural network. And finally, we introduce our convergence results. Setting interaction times and the network parameters appropriately, then we generate the data using the empirical risk minimizer over sparsity constraint neural network class. Then estimation error in the total variation is bounded by this quantity. So n to the power of -s over 2s plus e. So this can be shown to the minimax optimal up to logarithmic factors. Here the minimax optimality means that any estimator, not only to the diffusion model, but also ZHANG or other estimation, any estimator based on any data cannot further minimize the total variation error for some Bezout space function. So we briefly explain the proof overview. Due to the time limitation, we mainly focus on the score approximation rather than generalization. So we want to approximate a score with a small neural network. In order to do so, approximation should reflect the assumption that P0 belongs to a Bezout space, and moreover, our approximation should be varied all over T. So in order to do so, we introduce a novel basis decomposition tailored for score approximation, which we call a diffuse B-spline basis. Remember that PT can be written as a convolution of P0 and the diffusion kernel. Then, since P0 belongs to the Bezout space, P0 has this kind of approximation. Then we apply this to here, and finally obtain the approximation of PT as this summation form. So here alpha j corresponds to a coefficient, and this part can be seen as a basis function in the d+1 dimensional, meaning that both in space and time, so d+1 dimensional space. And we call this as a B-spline basis. Then we show that we can approximate this diffuse B-spline basis with a neural network with a logarithmic size, meaning that very efficiently. And similarly, we approximate number PT and obtain the approximation of the score following this relationship. Now finally, we obtain this bound at each time t while using the one same square neural network. So we do not need to switch the neural network. And finally, we derive the final approximation bound. The total variation distance is decomposed like this. So two truncation losses here are sufficiently minimized by adjusting the truncation time over line t and underline t. So the main problem is the score matching loss. And when we use the score network with at most n large n non-zero parameters for score approximation, then the bias and variance term of the score matching loss is bounded by this. Thus, balancing this bias variance trade-off, we obtain the final estimation rate. Okay, so now we further proceed to the analysis under manifold hypothesis. Let us consider the distribution supported on the low dimensional, say d-dimensional plane, and on that plane we assume the target distribution belongs to a Bezoar space as previously. Then we consider how close the generated distribution gets. And because this time, estimation distribution can never be absolutely continuous to the target distribution, we use the Wasserstein distance of order 1 instead of a total variation distance. Then we can show that for any fixed small positive constant delta, we can train a score network based on n data so that generated distribution achieves the following rate of n to the power of minus s plus 1 minus delta plus over 2s plus d dash. So this is known as the minimax optimal rate up to delta. So remarkably, in the exponent of n, the intrinsic dimensionality of d dash appears, not the full dimension d. So therefore, diffusion models probably avoid the curse of dimensionality in this setting. And moreover, this minimax rate in the Wasserstein distance is faster than that of the total variation distance. So the minimax rate in total variation is here, and Wasserstein is here. So the analysis should be much involved, but we did not get too much into it because due to the time limitation. So let me conclude this presentation. So we analyze diffusion modeling by regarding this as a distribution estimator and applied statistical running theory. The surprising point is that empirical score matching, this is the square loss minimization except for sparsity constraint, and therefore empirical score matching is computationally easy in practice. But this suffices to achieve the minimax optimal rate as a distribution estimator in theory. So we believe this compatibility of practical simplicity and theoretical superiority is one of the strongest benefits of diffusion models. Also, we prove that diffusion models can adjust to a low-dimensional structure of the true distribution under manifold hypothesis and avoid the curse of dimensionality in that setting. So we expect these results advance theoretical understandings of diffusion modeling. Thank you very much.
Thank you. Thank you very much. Any questions?
Hi, I'm Ivor. So I have just a quick question, right? So, do you have any sort of empirical validation of the bound, like for instance, how high it is, even in say small dimensional spaces?
Unfortunately, we do not conduct any kind of experiment. But one possibility is that one possible direction is that to consider 2 or 3 dimension, where the optimization is very easy because we assume the optimization error is sufficiently small. So in order to that to be satisfied, we need a small dimension. But we consider a very complicated function that gives a lower bound theoretically, and prove our several results. That is one direction. And I think the another direction is that when we fix the intrinsic dimension and increase the other dimension d minus d dash, that will be beneficial to exhibit the how manifold assumption is behave in the practical. So this is what I am considering, but up to this time we do not have any experiment. Thank you.
May I ask a question?
my question is about application. Since your method will adapt to a low dimension data structure, do you think that it can be used for the knowledge distillation from one distribution model to another distribution model?
I think that will be possible, but currently we are assuming the plane, so low dimensional plane, as a manifold, the simplest case of manifold assumption. So I'm not sure this can be extended to a more complicated case, but at least if the two distributions shares the same plane, maybe the, how can I say, the second distribution can be easily done in terms of sample complexity. But I think at the same time, I think that most of the work on that line of research focusing on the optimizability. So maybe considering how to optimize the score matching will be another direction. So this is my answer. Is this answering your question? Thank you.
One more question.
Thank you for the great talk. Recently, Nicholas Catini has uploaded a paper to archive and showing Nicholas Catini, the father of adversarial training.
I see.
Yeah, they show something very counterintuitive because people believe that diffusion models should memorize less training data than GAN due to the training mechanism. But surprisingly, if they use a membership attack, and then they show that diffusion models really memorize more training data, maybe 600 against 200 in a few million training data. So when you introduce the theoretical results, you said that it's already min-max optimal. That means the upper bound is also almost the lower bound, including GAN and not only diffusion models. So this means we cannot do better in terms of some privacy concern that we cannot memorize the training data because the training data may be like a copyrighted something like that.
Thank you very much. So in terms of the min-max optimal estimation rate, in fact, some training procedure of GANs also attains this kind of min-max estimation rate. So in terms of that, there's no difference if we just look the estimation rate. However, I think the training procedure are quite different. So they need to solve a min-max problem, but we only solve the minimization problem. So in that sense, the training procedure are very different. So I think that is one reason that the diffusion model can memorize much more samples. But yeah, the one thing I'm considering the robustness analysis. But yeah, because the usual theory for finance and minimization can be applied. But maybe the minimization problem that empirical score matching uses is quite classical. So we can expect much more well-developed countermeasure to that kind of adversarial attacks. So, but yeah, in this time, up to this time, I think the diffusion model is a emerging topic. So that is mainly why.
I guess indeed, GAN is already very well developed, but the diffusion model is still young, so it has potential. Thank you.
Thanks again for Kazusato's great talk.
Okay, so today we have many interesting talk like with robust AI, substantial AI, AGIs. So basically, this talk is about robust AI, how to retrain the machine learning models with multi-labels. So we know that nowadays the deep learnings have to read a lot of big data in order to have a good performance in different tasks. Okay. So today I'm trying to adjust the power bound for the logical problems. Indeed, I think RIKEN have done a lot of work on this. For example, also with myself, for example, Ivor and ZHANG all this work with Masashi Sujiyama, also we've done on many papers. For example, we have one of the highly cited paper of these co-teachings. and also using the transition matrix to do the robust update for this data models. So this work actually is based on our recent external data in Mengmi this year. So we try to give a Bayesian perspective to understand how this noisy label learn to solve different problems in different problem settings with practical applications. So we know the deep learnings have to be a lot of the big data, but those data actually may not be reliable. For example, in the internet, we have a lot of data. Basically, from the study we know for image learning, they have around 6% of the noisy label here. Okay. So for medical diagnosis, maybe even for some experts from those strategies, so maybe they also say around 15% inconsistent annotations. So for some autonomous drivings, maybe the errors is between 20 cms for annotations. So apart from this, I mean, for example, you have the large-scale data for these video QA problems. Okay, maybe there are 40 billions, which is very large database. Usually, we have to downscale the problem maybe to a small one to do some post-tracking. So because the sampling will introduce different bias here. So all this will affect your learning models. So how can we address these problems in a holistic way, or principled way? So this is the talk today. So I come back to the survey we did with Masashi Sugiyama, Lugan, Hambo, and here so on. So basically, we can understand learning with noisy labels like this. We can have 4 solutions. For example, we can have the noise transitions. So that means we can try to adjust the transition matrix for the classifications, and then we use these transition matrix to help to have a robust learning model. Or we can do some sampling to weigh the samples such that we can reduce the bias. Or we can do some model visualizations, try to adjust some decision boundaries to be more smooth. Or we can try to propose some robust loss functions. So they are the 4 typical methods to handle this noisy label. Okay. So indeed, if you're interested in more different category, you can come to our survey data on these label noise representations, past, present, and futures. Okay, so now I try to give you a summary on existing methods. What's the drawback for different approach? For example, the most simple one may be this approach, just two-stage approach. We just use some P-string classifier to learn the transition matrix, and based on this fixed transition matrix, and then we can learn a new classifier. But again, it is one-stage approach. The quality of initial transition matrix may not be reliable. Okay. So we can do something better. For example, you can introduce some single layer neural network to inject between the noisy labels and bunch of labels, okay, such that we can try to adjust some noise. Again, these problems may not be reliable. Okay, so maybe more reliable one, maybe you can using some EM approach. We try to estimate this transition matrix and update classifier, and then we update the transition matrix again. So we repeat this process until converge. However, this approach will be quite expensive. Another recent approach is so-called instance-dependent approach. Okay, so in this case, the noisy label Y will depend on output X. Okay, and then we try to learn the Y based on this model. Okay, so this is one of the most powerful models nowadays to solve this noisy label problem. However, such decouplings introduce a lot of parameter estimations, and this decoupling will be NP-hard. Okay, so it's very difficult problems to be solved for practical large-scale datasets. Okay, we come to some definition mathematically. So basically, we can define. Okay, so this is the prediction probability, and it is the transition probabilities given the dataset, and this is the noisy labels distributions. So the idea is like this. Can we use the data to learn the statistics to represent these transition matrix, and then also estimate these classified at the same time and decouple the dependencies? Okay. So we can introduce these graphical models. So X and Y are observed, theta Y observed, this is noise label, and Y, it is unobserved bound truth label. And then the Y is basically the parameter for this transition matrix, depending on the hyperparameter alpha. So we have K parameter for K classes for any sample here. Okay. So this is this setting for this noise label learning. Okay. So if you come back to the all methods, for example, SAM or stochastic gradient descent or atoms, basically you can imagine the update like this. You have the parameter for the real network, and then you have some gradient like this, and then you try to update this up. So imagine if your transition matrix is incorrect, so this update will be really unreliable. So how can we update both transition matrix and weight parameter at the same time to be reliable? So one condition like this is, okay, these gradients must be bounded. So we observe that if this gradient is bounded, we have high chance to learn this neural network reliably and safely. So how can we do this? So we come back to mathematical formulations. If we want to learn all the samples, we learn this Y, and the transition matrix will have these stored distributions. And if we factor Y, the distribution will be like this. And if we want to estimate all these parameters, will be expensive. You can see each update will take n times k complexities. Okay. So if n is now sent, it will be very expensive. Okay. Even you have to store a lot of memory, or if you do sampling, actually this problem also very expensive. So here we have some key idea like this. Instead of estimate these joy distributions, actually we can take some advantages based on the tips sampling. Okay, so that means we compute this p, y, n, given y negative n here. That means we try to take out this sample from the total distributions and then compute these predicted distributions. So with some simplifications, actually we can decouple the classifier distributions and this conditional transition probability. That means we can update both classifier and the transition matrix independently. And the computation complexity will quickly reduce to n plus k squared. N is the mini batch size. So that means we can efficiently update this model without any harm. Okay. So basically, we can represent the model like this. Basically, it is similar to traditional deep learning model. We have the images, we have the this classifier network, and then we can also have this Bayesian noise model here to model the transition probability here. So basically, each time we can just sample from both sides, and then we can update based on this formula. Okay. So we have both backward and forward approach to update this problem, and based on this deep sampling algorithms, we can update these two network efficiently. Okay, so here I just show you some results. So basically, we prove that, okay, with these updates, basically we can find the update for. So basically, this phi new minus the phi o is the difference of the update for each iterations. Based on these 3 and Fourier 3.1s, we can find that, okay, so the changes will be small, and you can see our results. So this is a training effort, okay. So you can see compared allocations, methods, the LCCN, the latent class conditional models. Basically, in blue color, you can see our update will be very stable with a continued update. But with you can see other methods, basically F adaptations, which is just update the upper layer neural network. You can see with continuous updates, the result will drop significantly. So that means those methods will not be reliable. We also try to show the comparison of FCCN and F application with different mini batch size. If you can see that, okay, for those other different methods, if they adjust the mini batch size to be very small one, you can see the changes of these transition matrices will be very big. But our method still bounded, okay, it's very small scale, okay.
So therefore, we can see a method basically propose safeguard mechanisms to guarantee each update will not do any harm to these model parameters. We also try to show that the transition matrix, okay, this is the initial one. With our methods, actually, we can recover the ground truth transition matrix. Okay, so there are some proof to show that, okay, the results. So basically, methods can converge in log n times, and then the transition performance basically depends on the gap between the logic and clean data, and then also the function complexity and the sampling size here. Okay, so so basically, we not only work on just simple multi-pass problems, we can also extend our framework to the open set settings. For example, here original parameter is k. So that means for k classes, we can learn the k times k transition matrix. But we can easily to extend the parameter to k plus 1. So we can easily to predict the out of distribution data or outlier here. Or we can also extend the problem setting to semi-supervised settings. So that means this branch of y can be partially observed. Okay, so in this case, we can also handle this semi-supervised learning settings. Also, for example, we also incorporate our co-teaching strategies. We can have this ensemble prediction here, so we can be even more reliable. Okay, so basically, we can generalize our graphical model to different settings here. Okay, so here we see some results. So FCCM is the basic model. So basically, we can see that it can perform pretty well here. And this divide FCCM is the methods we combine the co-teaching together. So we can see in this CFAR 10 and CFAR 100 settings, we can achieve the best performance and in different level of noise. So we can see even in 90% noise, we can also achieve pretty competitive performance against other baseline or state-of-the-art methods. So, okay. So here is symmetric noise setting and asymmetric noise settings. So we can see our method is very reliable in different settings of noise for these two benchmark data sets. So here is a setting we apply in this open set settings. So that means we have some classes to know. And then other methods, for example, in this setting, actually LCCN already outperform all the state-of-the-art methods. And you can see if using the LCCN star, basically is a setting considered open set settings, achieve better performance. And then also, if we consider the semi-supervised setting, also further improve. And divide LCCN basically is pretty reliable in different noise settings. Okay, so apart from those benchmark data sets, actually we apply on some very challenging real-world data sets. For example, Go1 millions and red visions, which is most challenging data set nowadays in these logic-level settings. Against methods achieve the best performance in all these challenging data sets. Okay, and here's some results that we showcase here. Okay, so here's some conclusions. So below many deep learning algorithms actually based on many assumptions have to tune the parameters to achieve good results. So here we try to give a mathematical understanding how we handle the logic labels and give a principal way to solve the logic label problems. Basically, we can constrain the update for these noisy transition matrices such that we will not do harm during the update. And then we also provide some visual properties to show the convergencies for our approach and give the transition band. And finally, we will also extend our framework to the open noisy settings, semi-supervised learning settings, and also apply for these cross-modal training settings. Okay. So which is very reliable, they apply in different kind of settings, and give you some explanation how can you achieve good results in deep learning training here. Okay, so my my students still have some ongoing work here. So basically, so we have solved the problems for multitask problems. So, but in this multi-label setting would be even more challenging. So that's mean one instance may be belong to multiple labels. Okay. So in this case, how can we define the transition matrix will be very complicated. Okay. So we still study how to do this. So if you're interested in this topic, please join me together to see how to solve these very complex problems, multi-label label logs. Okay. And also how to handle these multimodal learning settings to voice as well. Okay. Thank you.
Thank you.
Thank you very much for having us speak up.
Yes, question.
Thank you for the great talk. For the transition matrix, I think usually we need to give some assumption,
right?
Class condition or transition or something. When you do this from the Bayesian perspective, it may be reflected by the priority distribution, right? So how to make using priority distribution or prior knowledge to impose such assumption?
Okay, so maybe I come back to the our graphical models equation here. So in the sense that, okay, if you given this parameter for this transition matrix, basically is the typical class.
Thank you for the very nice talk. How do you plan to handle the multi-label?
It is a good question about this. So therefore, I assign this task to my students to handle this transition problem.
There are already some papers about multi-label.
So what do they use and how do you handle it?
Do you have any suggestions? You're expert in the area.
I think there are two types of noise. One is that it's regarded as binary noise.
Right.
But then it's very difficult to consider the label correlation.
Correct. Yeah.
Yeah. And another model is that they consider some object existing in this image is labeled as another one. Then it's quite similar to the multiclass.
Right. So for first one, I think because assume all the labels are independent, so may have a lot of error. So for second approach, I think it's quite promising. Maybe we can have further discussion on this.
Yeah. For the first one, even if you consider because when you estimate the binary transition matrix,
right,
you regard all the labels to be independent. But when you turn the multi-label classifier, the predictor, you don't have such assumption, so the performance is still fine.
Right, but the question is how can we robustly estimate these transition matrices? If you make assumption they are independent, then we will not estimate this
yeah, but my point is that because every transition matrix is just a binary, and you only have two parameters. Then that means if you have k classes, k labels, then just have two k parameters to be estimated. Then even if you have some relatively large estimation error for the parameter, then the trained neural network is not necessarily very bad. That's my point. It's more like a error tolerance of estimation error of the transition matrices. Yeah, but of course, maybe it's better to consider the label correlation.
Right.
When we estimate the transition matrices. But now, I must say it's usable. It's not optimal, but it's usable.
Right. I think another promising approach is we consider the dependency here.
Yeah.
Therefore, we can further enhance the estimation accuracy here.
Okay. Yeah.
Okay. Well, I mean, this is very clear model assume all these 5 parameters are independent. So one promising approach assume, okay, there are some dependency we can estimate.
Yeah. I think maybe you can also try to introduce from X to Y or from X to Y in order to handle instance-dependent noise under some Bayesian perspective.
Correct, but it may be even more complicated to do the deep sampling. But I mean, we can try basically. Yeah.
So I was actually
some time ago, a long time ago. I was actually involved in some kind of multi-level model using vector value RKHS actually for the matrix, the kernel matrix is actually right. So each kernel matrix value would be each kernel value is a matrix. So the kind of the label correlation is embodied into this output kind of kernel matrix. I'm not quite sure what it might be some relevance to this using vector value functions.
Yes, so what you mean basically you can use the label dependencies to learn the independent bases. Therefore, we can assume each bases are independent. Okay. So I think it is another formation approach we can explore. Indeed, it is somewhat, I think it's interesting to do. Thank you. Yeah. Thank you. This is the most important part. Yeah. Sure. Right. So I think today we have very good summary to talk about different topics in the 3 pillars from CFAR's key research area. I mean, so actually you should also in the modeling also talk about a little bit on this. We have this AGI, resilient and safe AI, and substantial AI. And today, Mengmi, Hwee have taught a few presentation on this area, particular introduce some concepts for this green computing, okay, and this cognitive science. How can we understand the attention from the eye and so on? So also, Xiaoli present somewhere on these challenges, opportunity in this substantial AI, and Chen present some using Fourier transform to do the updates for this resilient and safe AI. And Zhou also present the SAM models. Okay, I think this is very interesting topics. How can we have some fast and robust models for deep learning as well? And even myself also talk about some basic understanding, how can we handle the lossy labels? So, so this is good topics to study this, because I think nowadays, although the ChatGPT is very powerful packages, but those approach still data-driven approach. That means if you have some noisy data, also attack, those ChatGPT foundation models still have error, still have some mistakes. How can we have more rational, reliable foundation models still a key? So all these 3 topics still remain. Yeah. So I think this is a longevity research directions we can explore. That's why we set these 3 pillars in for CFAR. Okay. So basically, CFAR is AI colleges within A-STAR. So we compose all these AI talents. Most of them actually today have either the part-time or adjunct faculties in universities. So they work on UIBL research. We also have many students, scholars, and scientists work together for these 3 areas. So basically, so now today I try to come here, try to convince you, okay, we have a good team in Singapore. So we try to define some partnerships to see anything can work together on some problems. So here's our team for the investigators. I mean, at least half of them have been here today. And then we also, for example, Masachi is also one of the advisory board in our center. So please come to our center to have more discussion for its research direction for us. And we also have adjunct members working in different directions. For example, we also artists working in manufacturing, also have some colleagues working on bioinformatics, medical image domain, but fintech domains, also the quantum computing domains. So basically, we have experts from A-STAR in different areas to do AI with their domains. Okay, so this is some current scientists and engineers within our CFAR. So we currently still a lot very big centers, but all of them are the top tier scientists, PI within A-STAR with the AI. So we have some top 2% scientists identified at Stanford University. So some of them have been present the talk already today. So I just try to emphasize that we have 3 key pillars. We are very keen to achieve some impactful results and define some grand challenges in these 3 areas. So, for example, in this AGI, I think Zhou and Mengmi have presented somewhere already. But I think somewhere also interesting, for example, now, how can we do this learning by demonstrations? we know one of the key modules in this ChatGPT is learning from demonstrations. So how can we learn those policy to update those models will be important. So here we have done some work to do the learning from demonstrations using the generative models. So that means how can we use generative model to generate some consistent and robust sample to teach the agents and have to achieve the performance beyond the expert. Okay, so this is some research we have been done so far, but we haven't applied this for ChatGPT. Maybe we can have even better models than ChatGPT. So I think some of the work have been done by Mengmi and Hwee and his team on these human behavior understandings for these robots. Okay, so so for resilient and safe AI, I think we don't touch too much detail. Basically, this one is discuss about the setting for more realistic setting. Instead of the white box model, we also consider the black box model. So in the black box model, we try to consider how to reduce the query to do the attack, okay, and the defense. And we also have some work from ZHOU is doing this 3D attack. So I mean, 2D image has been done a lot already. Then this is a relative new setting. Also, we have some scientists working on very practical setting like this. Instead of consider the noise in these pixel levels for those images, we also consider the computational photography. We try to consider different parameters of physical effect for the images. For example, motion blur, shadows, green, snow, and some different effect to attack those visual system. Okay, to apply in different settings. For example, tracking, face, landmark detection, 3D detection, and so on. So we also have some work on these differential privacies. So we know this is very interesting work to protect your privacies, leakage, but we know those differential privacy is based on assumption of ID. So we also try to protect your privacies, leakage from your neighbor. So to do this, we have to define these differential pairwise privacies to protect against this leakage from your neighbor. Okay. So it's stronger protections for your privacy information. Also, we have some work, also some of working with Masachi here is working on these EEG signals. How can we extract the information from your brain and then to do some robust analysis? For example, here we apply in this application for the mental fatigue monitoring. So, so the previous EEG detection is offline because those data usually are very sensitive and very personalized. So it's very difficult to do the calibrations for those online settings. But we propose very robust approach to do online update. So therefore, we can do robust online updates for each signals applied in the real settings. Okay. So this is some work we published in this neural computations in 2020. Also, how can we do explainable AI? For example, we know when we have new concepts, these new concepts may not appear in training sets. So we try to understand this concept by parts. So we also develop this deep learning by parts. We try to understand the different components before we make the decisions. So we have this model to understand, for example, facial expressions or some flagging predictions for the bird. So we can see, we can understand this bird from different part of the bird and then to make the decision. Because to understand different species of bird will be difficult because they have subtle and mini difference. Okay, so which is not that trivial. Okay, so this sustainable AI, I think I don't go through too much detail because Xiaoli have very good summary overview on this already. So basically, below the transformer basically will consume a lot of energies, will have a lot of emission on CO2 gas. And but this is some important effort from Singapore. We have Singapore Green Pact 2030. We try to achieve the carbon zero, but we know which is very ambitious target we want to achieve. But I think every individual here are part of the world. We should work together. how can we apply the AI technologies to conserve the Earth, which is very important. So from this pipeline, we identify some problems, for example, data efficient AI, data augmentations, energy efficient AI, or also the transferable AI would be very important topics we can work together. I think you're welcome to drive together. Tens of samples to achieve the optimal performance based on these deep active learning technologies. Also, some of the team members haven't come here today. So he's working on physics-informed deep learnings. So basically, we know those physics domain knowledges, which is very important to provide some high informations. We can use them as regularizations. With such strong high informations, actually we can reduce a lot of training sample. So therefore, we can achieve good performance on those scientific problems with those physics knowledges. I think some also mentioned about this model efficient learning. How can we do the pruning? But here we try to emphasize that we try to do these methods with the consideration of the power consumption. Okay. So how can we reduce the power consumption? It's not directly correlated to the number of parameters here. Okay, so I think we also mentioned this, we'll organize this attribute conference on AI this year in Silicon Valley. So the deadline is still not yet, still open. Okay, so you still can submit paper there. And next year will be in Singapore. I think you are welcome. I mean, Masachi is also the program chair next year. You are welcome to submit paper here to organize a workshop here in Singapore. So we can work together for this new conference.
Holding a workshop would be a good idea.
Right, yeah. I think we can adjust both we can or some other society from local university, from Japan, or even from industry as well, yeah. Again, just some advertisements. Okay, CFAR also actively hire some early career researchers. Okay, if you have some postdoc, okay, have problem to getting visas, okay, so please inform us. Okay, so we have some position available.
We'll help you to babysit them together
to share the talent. Okay, so apart from these postdoc positions, scientific positions, we also have some internship scheme, teacher scholarship scheme to support those students. So you should also mention this morning we have, for example, we have some internship program. For example, let's say some student do PhD in Japan, they want to come to Singapore to do some internship or attachment for 2 years. So we have this ERA program. We also have some support from our center to support this joint supervision on PhD students. We also have some internship to support the undergraduates or master students as well. Also, we try to encourage some of the researchers here to visit our center. We have some support for those visiting positions in our center. Okay, so also just mention, around 55% of our PI are faculty or adjunct faculty in local universities in Singapore. Okay, thank you.
Thank you very much.